Hello, good evening, all. We will start the session after 3 minutes.
Good evening, sir.
Okay, so am I audible? Is my voice clear?
Clear, sir.
Okay, fine,
Yes, sir.
fine. I don't know what has been the issue with this YouTube live streaming since maybe last 1 or 2 weeks. It's not live streaming some way.
Sir, some people must have joined using a non-IITM email.
Does that affect live streaming? I mean, initially it didn't affect, I think, because
Yes,
we.
didn't initially. So I don't know.
Anyways,
So everybody is ITM. I think there's nobody.
uh,
Yeah, we see a symbol next to Prasid, but Prasid is probably using the regular ITM address. It's only one visitor it says.
wait, I'm checking something.
Prasid.
Just give me a minute. Uh, what does this thing? Anyways, fine. We will be recording the session as usual, and we will upload it by hopefully by tomorrow afternoon or so. Okay, nice. So let's start the session. Today is week 9. Fine. So we will today we will be actually starting with this week 9 content, which is basically another way or approach of programming. So this is one of the styles of programming. So let's start with that. Uh, So as you can see that your greedy was one way of writing program, right? One methodology of programming. Likewise, your let's say divide and conquer is another methodology of programming. Similarly, so dynamic programming is a separate methodology of doing programs. Okay, so or let's say another approach of doing program. Now, first of all, let's have the motivation of why dynamic programming came into, let's say, the existence and what is it all about. So see, the thing is, let's say you face a real life problem, right? You have to write solution for a real life situation or real life issue which is there, for which you are writing a software, and you have to think of something, think of a way to solve that problem. So how you basically do, the way that it is actually done is, at first you will try to solve the problem in a brute force or trial and error manner, because I mean, whatever algorithm we are learning here, you were discussing any algorithm, I mean, a specific algorithm or specific way to solve a problem. But when you face real life problem, things are not that simple. Most of the time, you will be required to deal with a lot of, let's say, mix up of different ways of solving. So let's say so to say, so a mix up of different algorithms like that, right? But so you don't know what to use and how to write it, and things like that would happen. So what you generally do when you try to solve a real life, let's say, a business problem, right? When I say problem, I mean you are trying to find an algorithm or a solution to solution to that issue which is happening. So what you try to do is, at first, make a, let's say, answer set, right? What are the possible answers, or what are the possible, let's say, solution to this problem. Now that you can do only by trial and error, which is basically brute force. You're trying to find out solution to a specific instance of the problem, and the solution to that instance is created by brute force approach. So this is the first thing that you do when you're writing a algorithm or a software, whatever you want to call it. So yeah, so once that is done, next thing is you try to figure out that, okay, if these are the solutions for this instance of the problem, then how can I reach to this solution? So getting the solution is a brute force and trial and error approach, depending upon the meaning of the question, or that is meaning of the, or let's say, the constraints which the question lays down to you. So on those you work upon, and you develop an answer set which by brute force approach, and then you try to reach those answer set, or I mean those answers corresponding to that instance of the question, by trying to find some algorithm, right? Whenever I say algorithm, what is it? What is an algorithm? Algorithm is nothing but an efficient approach of solving a problem. So you try to, so now you have solved the problem in a brute force manner, then you try to see the answers and backtrack your way to the problem. So basically, by seeing the answers, you try to backtrack how to devise an algorithm to come to these answers in a efficient manner. That's how you do it in real life. But let's say in this approach, you try to think, let's say, a week or a month or something like that, depending upon how much time your manager gives you. So but you couldn't come up with something nice. So what to do now in such a situation? You know that I'm not able to find any proper efficient algorithm to solve the issue, and also, it's, I mean, if I do trial and error, then that is, I mean, it's meaningless, because it would be exponential time. Trial and error, most of the time brute force approach will be taking you exponential time, because as you can understand, let's say, even if there are, let's say, two options for a situation where the input size is of order n, right? Order n means the input size is, let's say, the input is in terms of n, so I'm saying the input size is n, right? As we have done till so far, the input is treated as an input of, let's say, input size is n, so same thing. So let's say if I say that there is a n size input, and even there are only two options, even if I consider only two options for each instance of the problem is there, so 2 to the power n possibilities would be there, that you have to check. That is the brute force 2 to the power n options would be there for you to check whether this is a which one of them is the proper solution to that instance of the problem. So brute force takes exponential time. Okay. So now here dynamic programming comes into action. Now see something, sometimes what happens is, some of the problems are such, I will discuss some of them. Those of you who have seen the lectures, you already know that some problems are such that okay, they would be taking exponential time. because there are so many problem instances, but there is overlapping instances between them. So let's say when you are trying to find a solution to the main problem, that main problem can be broken down into multiple sub problems, and there is an overlapping sub problem property in that question, or in that problem, whatever you want to call it. So what do I mean by overlapping sub problem? So if I want to give a particular example, so let's say the Fibonacci numbers, right? So we know that how to calculate Fibonacci is Fibonacci n equal to Fibonacci n minus 1. So your f of n is equal to f of n minus 1 plus f of n minus 2. So this is the recursive equation for Fibonacci numbers, right? Now, if I just take an example and see it, so let's say Fibonacci of 9, if I make it like this, so it would be broken down into two Fibonacci. So Fibonacci of 8 and Fibonacci of 7. And 8 is further broken down into Fibonacci of 7 and Fibonacci of 6. Right? 7 can be broken down into Fibonacci of 6 and 5. And likewise. Right? So as you can see now that there is a lot of repetition of, or let's say overlap of the sub problems over here. Okay, fine. I will not continue this. So let's say this all goes on. So let's see from here. So Fibonacci of 7, this whole subtree, right? Whatever happens below this till the end. So this whole subtree is actually similar to this subtree. Whatever happens over here. Right? So as you can see, this whole part, this how much, I mean, this is quite a large part of the tree, right? The whole tree, this whole thing. So this whole thing is repeated. So if I calculate it once, f7, so I don't need to calculate it for the other subtree. So if I calculate it here, I don't need to calculate it here again. So I would substantially be, I mean, reducing my number of iterations, or number of, let's say, the number of time the program runs by this many number of iterations. So whatever is the number of iterations, I mean, sorry, whatever is the number of function calls over here, so many function calls will be reduced. No need to make so many function calls. Right, if I calculate the f7 over here once. So this is what we call overlapping sub problem. So in order to calculate f9, I needed to calculate f7, but f7 is there 2 times, and therefore I am only calculating it once, and the other time I will just use the calculated value done previously. So this is what we call overlapping sub problem property of a question or of a problem, right? The second thing that comes into I mean, that is very important over here is, which is what we call the optimal substructure property. So the first is overlapping sub problem, that is, you must have some overlap of the sub problem, so that once, I mean, you will only do that sub problem, solve that sub problem once, and later whenever that sub problem is again asked for, you will just supply the value of that calculated sub problem. So that will make your number of function calls lesser, and the program will be faster. So this is overlapping sub problem. Now what is optimal substructure? Optimal substructure property means solution of, let's say, each of the sub problem will contribute positively to the solution of the larger problem. So this is something like your divide and conquer concept. So if you, after dividing, if you conquer the smaller sub problems, right, then that is actually helping you to conquer the main problem, to, I mean, to get the solution of the main problem as well. Sometimes it might not be that, because let's say in greedy approach, right, greedy approach doesn't work in all the cases. Why? Because if you take the best possible choice which is available to you right now, that may not be the solution for the, let's say at the optimal solution for the bigger problem, right? Greedy, that's why greedy doesn't work in all the scenarios. It will fail in different scenarios, because that's the point, that if you choose something now which is best of your interest, it might not serve your interest in the longer run. So in those kind of problems, greedy doesn't work. So something like that, if optimal substructure, what it is trying to say is, if you try to solve the smaller sub problem, in some problems it might so happen that they will not contribute positively to the solution of the larger problem, right? But in some problem it might be so that solution of the smaller sub problems contribute positively towards to reach to make to the solution of the larger problem, right? So those kind of problem which has first overlapping sub problem property, and second solution to those sub problem helps you to reach the solution of the larger sub problem, which is optimal substructure property. These two properties, if these two properties are there in such a problem for which you are not able to find an efficient algorithm and you are only stuck with brute force approach, so in those kind of algorithm you can apply the dynamic programming concept. Okay, so that is the whole story. So you started with the real life problem, you couldn't find any proper algorithm to do that, so there is only brute force approach is the only thing that you have. And then what you would think of is, let's say, okay, it is brute force, that is fine, but let's see that whether those all the use cases within that brute force approach, is there any overlapping between those cases, and are those are those cases in such a way that if I solve one small case, will that help me to reach my larger goal, right? So if these two properties are there in the solution of the in that brute force approach, or let's say in the instances of that problem, then what you do is you go for dynamic programming in such a scenario. So let us now come to what is it all about dynamic programming. So it is nothing but brute force with a memory. I personally try to put it in this way. Dynamic programming is nothing but brute force approach with a memory. So when I call memory, what do I mean? The thing that I mean is, so like I said here, that you're storing the value of f7, you're calculating f7, let's say here once. So once you have this f7, then next time whenever f7 is asked for, you will not calculate it. You will directly supply it because you have calculated over here, right? Over here you have calculated, so you don't need to do it again. Whenever it is again, needed, you will just supply the value of f7 because you have stored the value of f7 somewhere after calculating it here, right? So that somewhere, that place is basically what I was referring to, the memory. It is brute force with memory. So in memory you have stored it, and whenever it is again asked for, you will simply supply it without calculating this whole subtree structure. Okay, so this is what dynamic programming means, and let me write the two important properties. First is overlapping sub problem. And second is your optimal substructure. Fine. So this was the plot of how it came into, let's say, in our course, or let's say in general algorithms. And now we will go into the finer details and see some examples of such problem. So before that, is the plot clear? Has anyone any doubt in this? Any points that you want to make?
What is this optimal substructure, sir?
Optimal substructure is that part which I talked, that when you are solving the smaller sub problem, it helps you to reach solution of the larger problem as well. That's the thing. Maybe in some problem it might not happen right like that, right? That is, if you try to solve a, let's say, a part of that problem, it might not contribute positively towards the solution of the larger problem as well. So that's where I gave the greedy example, that greedy doesn't work every time, because in greedy you are trying to solve, whatever best option you are having at current position, right? And that might not help you to reach the optimal answer of the whole problem at the end. In those kind of problem where greedy doesn't work, this is the case. So that's the point that I want to. So this is an analogy of greedy kind of non-greedy kind of approach, because in those areas where solving a smaller sub problem doesn't contribute positively towards reaching the larger main problem, in those kind of scenarios you cannot go for dynamic programming, right? So the property of let's say the property of a problem where solving the sub problem of that larger problem helps you to reach the solution of the larger problem as well, is what we call optimal substructure. So the substructure is optimal. That's what it means. So if you break down the problem into its structure, that is you're having multiple sub problem, then solving them optimally also helps you to solve the larger problem optimally. That's what optimal substructure means.
So
Okay.
that is recursion, right? That is where recursion comes in.
that is where recursion comes in. But as we will see in the next part of the discussion, that you can also do it in a different way. You might not need recursion all the time. Recursion is one way, another way is there. But substructure property is common in both the instances. It's a property of the problem. So let's say I would come to this point, that is our next part of the discussion, that these kind of problem where basically the thing that I discussed, it's kind of a brute force approach, but you want to, I mean, there is a repetition of the sub problems which is happening. So in such problems, you go for this approach of dynamic programming, or I mean this way, right? Now there are two ways of having the or let's say solving these problems. So one first way we call memoization, and the other one we call dynamic programming. So you will see that memoization is all about recursion and all, and dynamic programming doesn't use recursion. It does the thing in a different manner. But so that's why the solution part, right? The solution part of the problem, there are two options. First is memoization, and the second is dynamic programming. But the question part, that is the real life problem that we are facing, that must have these two properties: overlapping subproblem, optimal substructure. Okay, so I don't want to directly associate with the recursion part, because recursion is only one way of solving these kind of problem. The other way is dynamic programming. The recursive way is memoization. I will come in details discussion about that.
Such problems can be solved in both the ways, memoization.
Both the ways. Yeah.
Any problem can be solved in both the ways.
Yeah. Any problem means any problem where these two properties are holding.
Okay.
Right. So these two properties are the problem, or let's say are the properties of the problem statement. These are not the properties of recursion or anything. These are the properties of a problem statement. So if you see a real life problem which is having these two properties, then you can solve it either by memoization or by dynamic programming. Okay. Now the concept of memoization and dynamic programming is same. I mean, there is not much difference in that. Only there is a little bit difference in how to solve basically the implementation part. There is a difference in the implementation part that we will discuss. That's our next topic of discussion. Fine.
So,
but yeah.
So I just wanted to make a small point. So based on what you learned so far, right, in the course,
yeah,
right? So recursion part is very clear. There is a repetition part, right? When we are talking about this optimal substructure, so we studied in a graph, there are nodes and vertices and paths. Shortest path in a graph from one vertex to another, right?
Yeah.
When we are looking at that, if I'm going from start S to V, that is actually unique. So if I find a small segment and find the shortest path, that path is actually going to be part of my shortest path from S to V. So essentially, let's say in S2 by target of S to T, there is actually one particular node that comes in. If I solve that sub problem, that answer is contributing to my overall answer. So that is actually a case of where we have optimal substructure. The other part is actually opposite. Let's say our question is different. Our question is find the longest path.
Correct.
Right. So then in a DAG, let's say, longest simple path in a DAG. Right.
Exactly.
If we do that, then we can't really break down the problem, and the optimality actually breaks down. Right. So I think, based on what you have studied so far, I think these two things comes to the mind, like where we can use potentially versus not.
Exactly. So as you have rightly pointed out, so if you try to solve the longest path problem, then taking this optimal substructure property or solving a sub problem, or so to say, in that particular case, let's say from the bigger DAG, you just try to create a smaller sub DAG or something like that, and try to find the longest path in that sub DAG, and then take another sub DAG and try to find the longest path in that, and then you try to sum up all the longest path that you have got till now for all the sub DAGs that you have, and then try to say that this is the answer for the larger sub DAG. So that wouldn't work. But if you try to do it for the shortest path, that would work. So as you have rightly pointed out, so these two are the contrasting example over here. So optimal substructure property doesn't help you to find, let's say your longest path in a DAG, but it will certainly help you to find shortest path in a graph. So yeah, that's exactly the thing. Fine. So now we will come to the solution part, that okay, if I see a real life problem which is having these two properties in it, right? So there are overlapping sub problems, and solving those sub problem also helps me to reach the solution of the larger problem. So these two things are there. If that is the case, then next thing is how we will solve it. So the solution can be done in two ways. By the way, so let's quickly answer one question, that if I see that f of n, right, in a Fibonacci number, if I have f of n, so as I know, I will go n minus 1 and n minus 2. So basically, I will have a many number of, so let's say if I don't have this repetition, so f7 here, also f7. Now, if every time I get some f7 or f6 or f5, whatever, I am calculating it from scratch. So if I do not store the value of f7 calculated over here and do not reuse it over here, so if I do not reuse it, then I will have an exponential number of basically your number of, let's say, function calls, or let's say exponential number of iterations. So that would be order of 2 to the power n, right? Because basically I'm branching into two parts, right? And my input size is, let's say, n. So it would be going in that kind of, I mean, so many nodes would be there. So that is exponential. But now in case of Fibonacci, let's take this example only, Fibonacci only. And if I try to solve, I mean, try to take this approach of overlapping subproblem is there. So I will store the value once I calculate it. And again, whenever it is summoned, I will just directly supply it. So if I take this approach, then how many unique computation is required? Can someone tell me that in Fibonacci of n? Right.
N.
Order n.
Correct.
Order n.
So it will order n, right? So you need order n, I mean, let's say computation, and let's say each computation takes you constant amount of time. Fibonacci is some constant time work, right? So that's why your whole solution can be done in order n time. But here, if you do not store it, it would take you order 2 to the power n time. So you see, there is a, I mean, it's a superb decrease in our efficiency. Superb increase in our efficiency or decrease in our timing, just by storing it, just by doing some bookkeeping work. You are not applying any intelligent approach, not something very tricky or nothing like that. You are simply, what should I say? You are being disciplined. You are just maintaining the bookkeeping. You are doing some bookkeeping, and that's it. This is the benefit that you are getting. Why I say bookkeeping? Because basically you're storing the value once you're calculating it and then supplying it later if it is required again. That's it. You're doing.
Excuse me, sir.
Yeah.
How is it order and can you explain it again?
So let's say if I'm asking you to calculate Fibonacci of n, how many unique, let's say Fibonacci of 4, right? So in order to calculate Fibonacci of 4, you would need Fibonacci of 3, Fibonacci of 2. In order to calculate 3, you will need Fibonacci of 2, Fibonacci of 1. And in order to calculate 2, you will need Fibonacci of 1, Fibonacci of 0. Right? So this is the scenario. So my question is, how many unique invocations are here? Right? As you can see, this is repetition. F2 is here, F2 is here. F1 is here, F1 is here. So how many unique invocations are here? Right? 4, 3, 2, 1, 0. Right?
4.
Yeah. So basically you have 4 unique, if I consider 3, so 0, 1, 2, 3. So 4 unique computations are here. So you just need to compute 4 functions. And if you can reuse it, so 1, 2, how many of 6, total 6 function calls are over here, but only 4 of them are unique. So if you do the function, I mean, compute the function 4 times and store the values. So the other 2 times between these, right? The other 2 times, whenever the value is being asked for again, you can just supply it. You don't need to compute it. So that's why
we don't count it, like we just say that it is n times, right? Because of O of n.
Yeah. Yeah.
Like,
So
even though it's not exactly 4 times, it will be called, but the recursion will not happen, right?
yeah, exactly. It would be called, but the recursion will not happen. What you will do is basically will simply check, will write an if statement in the recursive function. I will show you the code. So before going into the recursion part, so let's say your recursion, whatever is the function, f1 function starts, and before coming into the base case and everything, right? So base case is here, let's say, and then you have the recursive case here with the return statement or something, right? So before going into any of this, at first you will write an if statement. So in the if statement, you try to, if or whatever, basically what you are trying to do over here is in the first statement that if, let's say I'm trying to calculate some ARR. So if ARR, let's say RI, so some ARR I is equal to, or let's say is not equal to none. So suppose initially the value was none inside each of the array. So whenever you are calculating a value earlier, right? And in the recursive case, let me just show you. The recursive case would be something like this. So whatever recursive function you have, so recursive function, right? That will be put inside ARRI. And then you return the value of ARRI. Right? So this is the way. You don't return the value. Initially what we were doing, you are directly returning this. Whatever recursive statement was here. So I would write return if, so you, how did you write Fibonacci? You simply return if n minus 1, if n minus 2, right? So this is how you wrote Fibonacci number, I mean, n minus 2, and here you will have the base case, and here is the function name. So you wrote this statement return. But now we will not write it in this manner. What we will do is rather we will put this value in f of n, right? Let's say whatever array you are using, ARRN, and then you return ARRN. Fine. And next time when you are coming for a, you will at first check if ARRN is not equal to, let's say, not equal to your some maybe initially you initialized all the array cells with -1, because that's not a valid answer. If it is not, that means it has already been calculated once, and I mean some value is there in ARRN, because ARRN has already been asked for initially. So now if I again get it is not equal to 1, that means it is storing some value, that means it has already been computed earlier. So then I will directly return. If that is not the case, else, so in after else you will do all of this. So all of this will be under else. So this is the recursion part. Sorry, this is the dynamic or let's say not dynamic programming. This is the main I mean trick of this whole discussion. So this is order 1 operation, right? So it will be asked for, as you are saying, correct, that function will be asked for, but it would not compute it. I mean, it will not go into further recursion. So that's why we will not consider it as one recursive call again, right? It would just return the value at that point only. Fine. So so why it is order n? Because as you can see, there are only always, if you have n as the number, then 1, 2, 3 up to n would be the number of distinct computation. And if you do order n those computation, then that's it. That's why it is order n.
Sir, instead of this array, we can use a dictionary also, no?
I'm not going into the implementation part. Whatever you want to use, you use. The main thing is that is you're storing it in some memory. Whatever data structure is fine with you, you can do that. Okay. So now coming to the solution part, how to solve this. So any problems with this property. So problems.
So we do it in real life, isn't it? Let's say in our hometown, we are going from one place to another. We open Google Maps or whatever, and we're going to unknown place. So then while returning, or whatever it is, right? Once you figure out a place which we know, let's say we are going to our house from an unknown place, right? So
Yeah.
once I reach a place that I know, then that is kind of a memory problem. Then I need to turn up the Google Maps because I already know the solution. I don't need to run the phone again. Right? Very similar to what we encounter in real life, where memory helps. We know how to
Correct.
solve it. Right?
Correct. Yeah. So all the problem which have these two properties, so we can solve it by memoization or dynamic programming. Now, what is memoization and what is dynamic programming? See, the concept is same. The core of the concept is this thing, that you have a problem where there are sub problems and repeating sub problems are there. So once you the first time that you get a sub problem, distinct sub problem, you will solve it and store it somewhere, and the next time when it is again asked for, you will supply it. So that's the whole concept. Both these solution approaches of memoization and dynamic programming exploits this concept. The only difference between them is how they exploit this concept. So what memoization is all about, it is about recursion. So it will use recursion, and it is basically a top-down approach. And dynamic programming is what we call a bottom-up approach, or let's say it will use iterations. Iterations means basically loops, and it is a bottom-up approach. Anything which is okay. So now what do I mean by that? So let's come back to the Fibonacci concept question only. So I want to calculate Fibonacci of 9. So in order to calculate Fibonacci of 9, one approach is what? Let's say I first start with Fibonacci of 8. Sorry, I mean, first thing is the first approach is memoization. So let's discuss that. So how will we do that? I simply using recursions, right? Simply writing Fibonacci in this manner, right? The normal Fibonacci function which you had. With that, if I add the property of storing the value somewhere, so that is basically exactly the function which I wrote earlier over here. So which is also there in your lecture, I think. Let me go to that part. Yeah. So as you can see over here, this thing. So this is your normal Fibonacci, right? Only these two statements are different. So this is the normal Fibonacci with this. If the key is already there, it has been calculated earlier, then simply return the, value. Or and here, if I calculate it for the first time, then you simply store that newly calculated value into a table, right? Now in this case, it's a dictionary, so that's what it is. So normal Fibonacci number, normal recursive function of Fibonacci that we have learned till date. With that, if I add these two lines, basically, then this is the memoization approach of solving the problem. Now, as I told you, the common concept remains same, that I will store the value somewhere. But what is the particular property of memoization over here? That I'm using recursion. As I told you, memoization is all about recursion. And why did I say that it is a top-down approach? Because if you write Fibonacci of, let's say, 9, as we had discussed earlier, so the first function call would be fib of 9, right? And then from fib of 9, I will go to fib of 8 and fib of 7. So as you can see, I'm starting from the top, and then the invoked function goes to the bottom by Fibonacci by reaching Fibonacci of 7. From 7, it will reach Fibonacci of 6 and 5. Likewise, I'm going to the bottom by starting at the top at Fibonacci of 9. Okay, but what would be the dynamic programming approach of doing the same thing? Right. So there, as I told you, we will use iterations, and that is a bottom-up approach. So how to do that? The thing is, in dynamic programming approach of solving the same problem, we will not start from f of 9. Rather, we will look at, in order to calculate any Fibonacci of x, right, f of x or fib of x, which values do I need to calculate fib of x? So if I say you, in order to calculate fib of 9, I need fib of 7, fib of 8 and fib of 7, correct? So what I will try to do in dynamic programming approach of solving the problem is, rather than starting from fib of 9, or let's say rather than starting from at the top, I will figure out what is required at the first step. Okay. So if I have the value of fib of 0 and fib of 1, so that would help me to calculate the value of fib of 2. If I have the value of fib of 2 and fib of 1, that would help me to calculate the value of fib of 3. And likewise, if I start from the bottom, right, like fib of 0, fib of 1, fib of 2, and I go up till fib of 9. So every two values, fib of 1 and 2, will help me to go to fib of 3, fib of 2 and 3 will help me to go to fib of 4. Likewise, I will go till fib of 9. So what is the first thing that I need? The initial values. So fib of 0, 1, those things is what I am starting my work with. So I will compute those values, and then I will use this function only, this expression only, but in the other way, right? I will go from bottom to top. I will go from fib of 0, 1 to fib of 9 by using these initial values of fib of 0, fib of 1, fib of 2. Okay. And that is the dynamic programming approach, and therefore we will use loop. So we'll start a loop from 0 and go till the end, and basically that's why it works. And it would get more clear when I come to the example. But that's the basic thing. That's the basic approach. So dynamic programming approach of solving this problem will use loops, and it will start from the fundamental. It will start from the very basic problems, basic sub problem, which is basically the root of all the sub problem, and it would grow up on that. So it will use those smaller the basic level sub problem to reach the higher level problems. That is your bottom up approach. So bottom to up approach by using loops. But that is dynamic programming. And what is memoization? You use recursion to go from top to down. So you don't worry about what are the things needed to calculate f of 9. I know that f of 9 is required, so I invoke f of 9, and whatever is required to calculate f of 9 would be invoked implicitly by the function. So that is the top down approach. So that is what we call memoization. Okay. Now the thing is, so as you can see over here, so dynamic programming is like this. You calculate f of 0 first, then f of 1, then f of 2, and likewise you go till f of n. Right. So that is the dynamic programming approach. You no need to right on my system. Just wait for a minute. Fine. Fine. So before proceeding with the next part of the discussion, which is some examples of this kind of problem, let me state one important point. So as it would get more clear as we see some example, but still I want to mention it now only. So as you can understand, dynamic programming part will use loops, and your memoization part will use the recursive functions. But they are basically doing the same thing. In a different perspective. One is approaching from top to bottom, another one is approaching from bottom to top. So dynamic programming takes care of all the prerequisites at first, and then grows up till to the final solution. Whereas top-down approach or memoization directly uses recursion, and that's why it starts from the main problem and then it finds its way towards the smaller sub-problems. So yeah, that's the primary difference. But other than this, one important point is which one is better. So in terms of performance, recursion is always a bad thing, right? Recursion, because in order to do recursion, you have to do a lot of internal system related bookkeeping work. So that takes some overhead. So because of that, if you are using recursion for smaller problem, then it is fine. It is always great. Recursion is always great with smaller problem. Why it is great? Because if you are using recursion with smaller problem, recursion is most of the time very easy to write or very easy to think of. So or very simple code is there in recursion. So that's why for smaller problem, that part is more let's say beneficial. But also the system related internal overheads doesn't matter much if the problem is if the input is smaller size. But if the input is very large, then let's say the benefit of let's say the benefit of simplicity of recursion doesn't mean much, because the system would take a lot of overhead to do recursion for a larger number of times. So that's why recursion is most of the time not seen with such good eyes in let's say algorithm performance. So that's why we will try to avoid recursive solution to problems, and that's why the memoization approach of let's say solving this kind of problem is mostly not preferred. Dynamic programming is the one which is preferred, because it will use loops and it would be very efficient, right? but the time complexity is same. So the thing that I spoke about between memoization and dynamic programming is particular to system related timing. But if you just ask the asymptotic time complexity, then it would be same for recursion as well as the dynamic programming approach, whatever you are taking, because that would primarily depend on the number of distinct computations that you are doing, the number of unique subproblem that is there for a particular problem. So that would be same whether you take the recursive approach or the loop approach. That is, you take memoization or dynamic programming. So that would remain same, and that's why your timing also remains same. But from a system related timing, not from asymptotic timing, dynamic programming is inferior. Okay, so now let's, yeah.
So memoization is more efficient than dynamic programming.
No, that's what I said. Memoization uses recursion, right? So anything which is using recursion is not should not be used most of the time.
Okay. In dynamic programming, though, we are doing the same thing, but we are starting from the base case, right?
Correct, and that's why we don't need recursion. We can use loops. You start from I equal to 0, right? And that's it, starting from
Yeah,
base
okay.
case.
So,
Okay.
so that's what we learned, right? Anything that is recursion, we can create a loop. I think only one thing is
Exactly.
primitive part. I mean, we didn't understand. I think somebody, I remember when we were discussing,
Correct.
I didn't make really understand that part, but most of it can be simplified.
Yeah. Most of it, in the sense, I mean, you can say that as of now, in our current, let's say, realm or whatever is within our uh, boundary of discussion, and I mean, you can say that anything, whatever is there, you can always convert a recursive code into the iterative code and vice versa. Only thing is, if you are going into theoretical research and all those kind of things, then there are a certain sets of problems which are, which cannot be solved in a iterative manner, because I mean they are highly recursive. So one such, I think I just mentioned. So one example, which is basically the different types of Ackermann functions. So if you see that, if you want to just check into what are those things, it's more from a mathematical point of view, or let's say research point, theoretical understanding point of view you are going. But so as to say, any real life problem, whatever is given to you, you can solve it by converting vice versa, from from your recursion to loops or from loops to recursion.
We actually encountered that, but I stopped. In Corman, actually, for the Kruskal, like when you do the union find,
Yeah.
that is where it is mentioned. And after looking at math, I stayed away. But
Yeah.
yeah, it is actually there.
Correct. It's a little bit kind of involved. Okay, so now let's take some examples. Enough with our motivation and discussion and what this and that and all about. So now let's take some example of problem where those properties hold and where we are trying to solve it. One important point in our whole discussion, we will be use dynamic programming. We will not use memoization. The whole discussion will be based upon the dynamic programming approach of solving the problems. That is basically the iterative or the loop approach of solving the problem. Fine. So first is this grid path. Now this is kind of your discrete math discussion a little bit. At least it starts with a discrete math kind of discussion. So the question is, you want to go from 0, 0 to 5, 10. How many ways are there? That's your question. Right. So number of ways to reach 5, 10 from the 0, 0 position. The constraints given to you is that you can either move right or either or up. So you can make a up movement or a right movement. Down movement and left movement are not allowed. Right. So how to do that? For let's say, how many ways are there to reach 5, 10? If you are only allowed up movement and right side movement, so you can either way take one, and every movement would be 1 unit length, right? So you can either make this movement or you can make this movement from here to here or from here to here. Right. See
So
on
50, right? So it will be 5 right movements and 10 up movements, and we can take a combination. So 50.
yeah, so correct, 5 up movement, 5 right movement and 10 up movement. That is exactly fine. But the question is, how many ways? How many? I mean, if let's say this is one way, right? I start from here. I can go like this one way, like this one way. There are many such ways, right? So how many ways are there? Is it 50?
I think so. No,
Yeah.
sorry, combination. Sorry, the first step can be taken in.
C5.
Yeah, so 2 ways. We have to look at the. So after every step, yes, it's there's a restriction actually.
Correct. See, 50 is when, what is the logic behind saying 50? So I have 5 right movement and I have 10 up movement. 50 will only happen if I multiply 5 into 10. Now, what does multiplication means in combinatorics? Multiplication means that for each, so let's say you are multiplying A into B. So that means for each use case of A, I mean, whatever is the magnitude of A. So for each one use case of that magnitude, I have all the use case of B. So whatever is the magnitude of B, that is the idea. So let's say if I'm multiplying 3 into 5, that means for each of the element which makes 3, that is 3 element which will be making the 3 as the count. For each of those element, I have 5 possibilities on the other hand. So that's why 3 into 5 you are doing. So when I say I am multiplying 5 into 10, that is 5 right movement into 10 up movement. That means for each right movement, I have 10 up movements that I can make. That's what that's what the statement part of this mathematical multiplication would come up to. So if I just stick with that definition, then what does it conclude? That if for each right movement, for each one right movement, I have 10 up movement. So that would mean that, okay, so if I take this right movement once, so I have 10 of movements in my option. So I can either go here or I can go here. I mean, let's say 2 up movements, so I will reach here, or 3 up movement, I will reach here. So fine. So I can go till this point. So 10 up movement. Whenever I'm taking
5 minus 1.
Now, since we are talking about dynamic and recursion, all those things, we will think of, instead of 5 by 10, we think of 4 by 10, 3 by 10. Ultimately, you come to 1 by 1. We'll find out for how many movements are required for 1 by 1.
Let's as what did I tell you at first? What are we trying to do? The first thing is, at first I have to find the solutions. That is basically by trial and error or mathematical some way. Forget about dynamic, that will come into later. As I told you how the progression happens, right? If you see a real life problem, you try to find the solution first. The solution instances, not the way to solve them. At first you need the answer. Once you get the answer, then you try to find a way to reach to this answer. So I first need the answer, a number, which is the number of ways from 0, 0 to 510. So okay, I will come to you again to get the answer, but let's discuss this thing at first. So if I say that for one right movement I have 10 up movements, so that basically means if one right movement I can reach to any of the cells over here, so that is fine. But in that case, do I have only 5 right movement? I mean, 5, I can consider the 5 rights over in this line only, right? So these are 5 right, but I can have the right over here as well, right? I can have the right. Okay, so that means whatever is the, these 50, so 5 into 10, 50 cells are there, so that means 50 right movement are possible. But then if I take 50 right movement, so for the right corresponding to, let's say, this position, right, do I have 10 up movements now? No, right? Because only one I can move only once. So then
once you get closer, edge will restrict you.
Correct. So you don't know. You cannot solve it in this manner. This is
before going to that place, you would have already taken 9 up movements.
Correct. But what those up movements are corresponding to, let's say, some other right which was at the bottom, right? So let's say this right which I took over here, and then you take this up movement to reach here. So this up movement is corresponding to this right if I do multiplication.
It's like a binomial. If I have taken like a total number of movements are fixed, if I take one movement, then the other one is restricted depending on how much I
correct. Correct. Like that. Yeah. So that means, that's the idea. So if you do that,
here can we move downward also? Means
no. No downward and left movement is allowed. Only up and right movements are allowed. So you see that whenever these kind of problems happen, you will understand that I might not be seeing the problem from a right perspective. So you have to change your perspective to reach to the solution. So into doesn't work, multiplication doesn't work.
It's equivalent of like backtracking. If you are going in a graph, right, going from vertex to another one, you want to go in the direction where your target is. So taking a left or a down is essentially going against the the direction where the solution exists, intuitively speaking, right? So
Yeah.
that's the restriction.
Either
That,
we will move left or right, or left or upward. So there are two ways
Correct.
in each step.
Okay. Then
Then ultimately, if I move 5 steps left, then I will have no option.
okay.
So for first 5 steps, there are 2 to the power 5 options, in which whether I move left or up, I do not know. So I think answer should lie somewhat here. My thinking is correct, sir?
If you are taking right, I mean, at first only you are considering you are taking right. Then the two options that you can go up or you can go right. I mean, so that would be wrong. You can only go up if you are considering right now. And then you have to also take care of, you can only take 5 right. You cannot go above that. So yeah, that's one issue. So let's
so one more point, sir. So here, technically, if I'm in the middle of the graph, we could actually move in 4 direction. In this specific example where the source is bottom left hand corner and target is right hand corner, we know that optimality exists in the direction of, if I combine right and upward movement. So essentially, out of the 4 possible movements, we restricted 2, so that way we narrow down and increase our chance of reaching the optimal solution faster. If we change the problem, let's say instead of going from 0, 0 to 5, 10, we go from whatever, like 0, 10 to 5, 0, for example.
okay.
Then the restriction would be, you can come down and right, but not up or left, right?
Yeah.
So essentially, the restriction again is a function of the specific instance or problem at hand, right? So there are basically 4
Correct.
degrees of freedom,
Correct,
and we're
correct,
restricting 2 degrees of freedom. Ensure that in our optimization one, we want to operate in a feasible space. Let's not get into another area where it will not drive us towards optimality.
Correct. But that is for a different problem set. So when the coordinates change. But for this, basically, we will always start at the bottom left corner, and let's say we need to move to the top right corner. So, so let's now get to the solution then. So, let me ask this question: how many ways you can arrange the letters of the word Mississippi? Is this question looking familiar?
Starts one.
I don't know whether the spelling of Mississippi, whatever is, maybe it is wrong or something. So this is quite familiar question, right? With, I think most of you would have. Factorial is fine. So how do you do that? What is the meaning of that? When I say that, how many arrangements are possible?
There are total 11 letters.
Permutation.
Yeah, 11 letters are there. So they can be arranged in 11 factorial ways. That's
But
all.
yes,
There is no restriction.
double S is there now, sir.
Yeah, so
Double S will, whether S1 and S2, if you take, both will be same only. So you have to
Correct.
subtract that.
Subtract?
Actually, no, you have to divide it by,
Factorial, 11 factorial, you have to divide.
you have to divide by the repetition. So there are S, which is repeating 4 times, and P and I also repeating 4 times, and P is repeating 2 times. So that means for all those repetitions, you have to reduce the combinations. So 11 factorial divided by 4 factorial times 4 factorial times 2 factorial. So that is what was in starts one.
There are 10 letter only, no?
11.
No, P has to repeat 2 times actually.
Yeah.
There are 2 P's, whatever it is. I don't care about the word. I mean, what I mean is, let's take this example and just do it with it.
Some Malayalam or something, Malayalam or whatever, right? That's
Then only
Well, okay,
4 factorial and 4 factorial.
So here 10 only are there in this example.
Okay, fine, no worries. So let us take any other word. Let's say
Malayalam,
some.
closer to home.
Okay, fine. Right. So here, what should be the answer?
9 factorial divided by 1, 2, 3, 4 factorial into 2 factorial into 2 factorial.
Sir, here M is appearing twice. So we should first do the frequency, and then L is twice, A is thrice.
4 times.
4 times, sorry, yeah, 4 times.
4, 2,
Fine.
2, 8.
That's it.
Correct.
8.
That's it.
Okay, so So we did this because we wanted to arrange the letters of the word Malayalam, but we saw that there are repetition of the letters within them, and that's why any such another, I mean, let's say another arrangement of both A's, I mean, starting with, let's say, a word starting with the two A's, we will not be able to differentiate between them. And that's why we did the division, so that all those kind of combinations are taken out of the question, right? So if I just make it in this way, I have 5 right movements. I have 10 up movements. So let's say up, up, up. And the number of ways to reach that coordinate 510 from 0, 0 is basically any possible intermixing or arrangement of this right and up movements. That is basically the same concept if you apply.
Yes.
So which is basically 10 plus 5 right, which is 15 factorial divided by 10 factorial, 5 factorial. Does it make sense?
Yes, sir.
Right. So the number of ways to reach from 0, 0 to 510 is basically any possible combination of these right and up movement. So if you do 5, you have at your, let's say, 5 right movements are there and 10 up movements are there, and any possible arrangement of these 5 right and 10 up movement will take you to the coordinate 510. The thing is, how many such arrangements are there? That's the question is. So you can do it in this same manner. Just you are mapping the way to solve these kind of repetition of letters problem to this approach over here. So this is basically the solution: 15 factorial by 10 factorial into 5 into 5 factorial to the number of ways you can reach from 0, 0 to 510. So that is done. Now what is the next part? Let us go to the next topic of discussion, which is
Sir, can we derive the method if we allowed other step also? It means left, right, up, down.
now if you go for up down, then the things change because for each, let's say, when you are going down or left, then basically you are undoing the effect of one right. Going left means you are undoing one right.
Infinite one.
Yeah, and going down means you are undoing one up movement. So if you are undoing and redoing something, then there can be infinite possibility. You can go 9 times up and then again come 9 times down, and then again go 5 times up, again come 5 times down. So you
So,
can
so
be, I
in
mean,
this problem, we are only going upwards and towards that 5-10 spot.
yeah, that's what I started the discussion with, right? Only up movement and right movement is allowed. That's it. You're starting from 0, 0, you have to reach 510, only up and right movements are allowed. How many ways you can go? Okay, so now the next thing is, let's say I have a block over here. So that means any road that passes through that block, I mean, basically any road which was, yeah, that passes through that block is closed for today. So you cannot go through the road. So what I mean is, let's say any road which looked something like this. So let's say this. So this road, right? So this road you cannot use. Or let's say another road is something like this. This one also you cannot use. So whichever is passing through this particular point, you cannot use that road for today. So if this is the new addition of complexity to our problem, then how many ways are there to reach 510 from 0, 0? So basically you can understand that I have the total number of ways in a without any block kind of scenario. So I have that, and I can subtract the number of ways that is passing through this block. So if I subtract that from the total number of ways, I will get the answer. So then what is how can I calculate this? So this can be calculated very easily. How we can do is, basically we will break the problem into 2 halves, right? The first half would be this much. Okay. So basically this is my first half and this would be the second half. So all I want to do is, let's say this is what? Tell me the coordinate value of this point. 1, 2, 3, right? 3 and 1, 2, 3, 4, 5, 6. 3, 6. So this is basically your 3,6. Fine. So what we will do is we'll try to find the number of ways from 0, 0 to 3, 6. And then we will try to find the ways from 3, 6 to 5, 10. Right? And then that means the number of ways I can reach from 0, 0 to 3, 6. If I multiply that with the number of ways that I can reach from 3, 6 to 5, 10, that means for each way over here, in this part of the question, the number each way over here, number of ways, I can take any one of the way over here, right? Any one of the way over here. So that's why I'm doing multiplication. So if I do multiplication, then I will get the answer of number of ways to reach from 0, 0 to 5, 10 using 3, 6. Right? Using 3, 6. Now, if I have that answer, all I have to do is subtract that using 3, 6. How many ways are there? Just subtract that from the total number of ways. So then you will get the ways which will not constitute this 3, 6. Right? So same thing. If you want to calculate this, what would be the answer? It would be basically your 6 up movement. So 6 plus 3 is 9 factorial divided by 6 factorial into 3 factorial. And this would be your 3, 6 to 5, 10. How many things are there? So 4 and 2, 6 factorial divided by 4 factorial, 2 factorial. Right? So you have these two numbers. So multiply them. After cross multiplying, whatever number you have, that is 9 factorial into 6 factorial.
Certainly, we have 10 ways, right? So why are we taking 9?
No,
We have
no.
0 to 9. Right?
0, 0 to 3, 6. How many ways are there? 1 way, 2 way, 3 way, and 6 plus 3, 9, right? Why 10 ways? You want to reach here.
Okay. Fine. So right and up, both options here combining. So they are steps, and that is why we are doing it like this.
Yeah. What was the main concept? The main concept was that if you want to reach from 0, 0 to 5, 10, let's say this block was not there, then I have 10 up movement and 5 right movement to do that. So that's why I did it in the manner I discussed earlier. Now my next question is, I want to find all the ways which passes through this block. So in order to do that, I'm breaking the larger problem into two sub-problems. What is the first sub-problem? The first sub-problem is, forget about this whole part. I mean, I'm only considering this much now. This is my problem. Okay, so this is the graph that I have. Now within this, I want to reach from 0, 0 to 3, 6. So that's basically the same problem on a smaller part. So how to reach 3, 6? Simply 3 up and 6, 3 right and 6 up movements are there. So you can do it in that same manner. 6 plus 3, 9 factorial divided by 6 factorial, 3 factorial. So once you have reached this point, the next thing is, how can you reach from here to 5, 10? That is the next part of the problem. Right? Another sub-problem. This sub-problem. So you do the same thing, just consider 3, 6 is at origin. So if 3, 6 is origin, 5, 10, what will you do? Subtract 5 minus 3 and 10 minus 6. Basically, it's shifting it to the origin. So that's why you get 6 factorial by 4 factorial, 2 factorial. Okay. So these two sub-problems you got. So the number of ways to reach from 0, 0 to 3, 6 is this, and number of ways to reach from 3, 6 to 5, 10 is this. Multiply them, whatever answer you get, that is the number of ways to reach from 0, 0 to 5, 10 via 3, 6. So this is your answer. This is the number of ways. Now the question was that how many ways are there where you don't have to go through this block, right? Because it is block. So the total number of ways was what? 15 factorial divided by 10 factorial, 5 factorial. Subtract this quantity. That's your answer.
So long random question right here.
Right? So this is the mathematical part of it. Now the next thing is, what happens if I have another block? Right? What will you do that in such a scenario? Same approach. Doesn't
What
make
is
a
the question now?
Sorry?
Sir, what is the question now for these two blocks?
Another block is there. Same thing. How many ways are there you can reach 5, 10 without going through the blocks?
Sir, if you think like graph, like let's say each intersection is a vertex, and each of the line is a street, and we are going from our house to a destination, right? So initially, when there are no traffic closures, we can take any path, any road, no problem. So that is the original 15 factorial by 10 factorial by 5 factorial. But now suddenly, there is, because of some reason, maintenance, they have closed that intersection. So now we have to find solutions or paths which does not involve those two
That's
vertices.
that's the point. But how to do that now?
Sir, I think
From
So
Venn
that
0
diagram.
to
only.
16.
First, we will calculate for
That,
1/6.
yeah.
First, we will
Then
calculate
for
for
3/6.
1/6. Let's do that. First, we'll calculate for 1/6, right? So how will we do that for 1/6? First, I will
7 factorial by
7 factorial
1
over 1
factorial by
factorial over 6 factorial.
7 factorial. 1 factorial is 1, so let's keep it at that way. 6 factorial. Okay, done. So after that, into number of ways to reach from here to here, right? To 5, 10. So what will that be? 8
That
factorial.
would be 4 plus
8 factorial by 4
8
factorial
factorial.
by 4 factorial.
Fine. So that is done. So this is for what? 1/6 part. Okay. Now same thing we'll do for 3/6 part. So that is basically your what the same initial 1, 2, 3, 9 factorial, 3 factorial, 6 factorial into 6 factorial, 4 factorial, 2 factorial. So this is what for 3/6 part. And the total thing was 15 factorial divided by 10 factorial, 5 factorial. So let's say this is A, this is B. So if I do this thing, is it correct or are we missing something?
No,
No,
there
this
can be
will
paths
we
which
have
can
both
extend
from
to
1 to 6 and 3 to 6, some other common
Correct.
element will be there, no, sir.
So what
So
will be the
something
issue?
A union B you have to do. A union B equal to A, N of A plus N of B minus N of A intersection B.
Sir,
Correct.
1 to
subtract
6
the
to
paths
3
which
to
go
6
from
to
0
5
to
to 10.
1/6, from 1/6 to 3/6, and 3/6 to 5.
Sir, this area from 00 to 16,
You have to
that
add, sorry, you have to
rectangle is
add.
common.
Add the paths which go from 0 to 1/6, 1/6 to 3/6, and 3/6 to 5.
Correct. So we have to do the addition. That's what I was looking for. So we have to add the path where both 1/6 and 3/6 are common. Why add? Because we are
Because we have subtracted it twice.
correct. So because all those paths which passes through both 1/6 and 3/6 are counted in A and B, both the cases. So when I am calculating A in that also, which the paths which passes through both 1/6 and 3/6 are counted or are accounted for in both calculation for A and calculation for B, because A means all the path which goes through 1/6. Obviously the path which goes through both 1/6 and 3/6 will be there in A, and also it will be there in B. So since it is there in both these terms, so when I'm subtracting A plus B over here, that time those paths which are common to both A and B are getting subtracted twice. That should not happen, right? Because that means a single path is subtracted twice. The same path is being subtracted twice from our answer. So that is wrong. So that's why you have to add a term. So what is that term? We will, since we are subtracting twice, we will add once, and that will undo the effect of 2 times subtraction. So that's why we'll do an addition of all those paths which are passing bit from, I mean, which is common, which is passing from 00 to 510 via both 1/6 and 3/6. Now, how will we find that? So that, let's say, to find that, what we will do is, at first we will go 00 to 1/6. So that is fine. How many paths are there from 00 to 1/6? That is
6
basically
factorial
correct. So that is basically your 7 factorial.
by 6 factorial.
Okay. Next thing
And from
is
1/6 to 3/6.
okay. So how many paths?
One path only.
Only one path, right? Because you can only go right side or up side. If you go up, you cannot come down. So only one path is there, which is basically 2 right movement, which is basically 2 right movements
Into 3 to 5.
correct. So 3/6 to 510 if I go, so that is 4 and 2, 6, right? This we have to add. Let's say this is C. This is your answer. Fine. So that is So you see that this is the complexity that we reach with only two blocks, that you have to calculate so many partial calculation, right? At first, for each block, you have to do two partial calculation. Then for both the block, you have to add the terms, right? Now, what happens if I have blocks, many blocks? If I have there one block.
De
We are
Morgan
not
laws.
studied it, that theory. We are not studied
De
this.
Morgan. De Morgan is remembering from stats 2 or 1.
So that's the issue, right? We cannot, I mean, it would be very tricky to solve such a problem. So now this is where we forget about mathematics and come to computer science. Okay. So here we will use dynamic programming. How to do that then? Let's come to the main point of discussion. So why we came into so much, so let's say why we discuss so much mathematics or something is we must be motivated to understand, okay, why if we have combinatorics, why do we need to go for this programming and all of that for such a problem? The problem is when you go for different, I mean, when the thing becomes scalable, when the number of blocks or let's say the constraints become heavier, then the ways to solve a problem becomes, I mean, analytically solving a question becomes very difficult. So that's when you need programming. Okay, so let's break the problem in, as we will now we will come to, as one of you mentioned, that now we have to think in terms of dynamic programming and all of that. So we will think that somehow we have to reach zero or some, I mean, how to do that. So now we will break the problem into smaller sub problem. How to think of it? So let's say this index, right? Let's take it as I comma j. Okay, one important point in this discussion in the slides, right? So generally we take I in loops, I mean our normal programming concept, we take I to be the loop row variable. So basically I travels downwards, right? And j travels on this column variable. So j travels this side. So this is our general convention of programming. But in this particular grid path discussion which we are doing here, in the slides we are taking I to be on the x-axis and j to be on the y-axis. Okay, like in physics. So your I would be taking, I would be going over here and j would be going y-axis down. Fine. I mean, you can just, I mean, some of you might get confused if you have this preconceived notion of looking at I as the row variable. So if you see these things, you will get confused later. So that's why I'm mentioning here I am taking I to be on the row and j to be on the column. You can interchange it, doesn't matter. Only thing is you have to take care of the recursive equation that we will write after this. If you interchange I and j, you have to take care of that thing as well in those equations. Fine. So
it is equivalent to that state space, Monte Carlo, right? So it doesn't matter.
yeah. So here if I consider this ij, I will think that how can I reach this ij, right? Just one step, go behind one step. Don't think of how can I reach ij from 0 0. That is the mathematician's thinking process. Computer science people don't think like that. They just think what is just the previous step. Once I figure out just the previous step, I will again figure out, okay, from that previous step, what is the next previous step? I mean, next means what is just the earlier previous step. Then what is the earlier previous step? So like that, one by one, I will go. So if I am at ij, how can I reach ij?
Diagonally downside that crossing, sir. I minus 1, j minus 1.
You can go right from I minus
1, j minus 1.
Okay.
You can go right from I minus 1 j.
Okay, so that's the point, right? So I cannot diagonally, so to address the point raised, the diagonally opposite. So let's take this point. So if I am at this area, I told you, tell me one step behind. Okay, so from here, can I go here?
No. You have to take two steps, right and up.
Yeah, that's where I said.
Yes, sir, correct.
That's
You
where I said.
Go right from I minus 1 j.
Or from down.
You can go from I j minus 1.
J minus 1.
Right up or up right.
From these two places, you can go to ij. From red to green.
Fine. So these are the two places that, all of this dynamic programming is based upon what is the next, either what is the next step or what is just the previous step. Don't think of the whole problem. So just think of one step earlier or one step, what is the next step. So think in that terms, because if you can figure out what is just the previous step, you can just repeat that concept to the previous step of that step, right? You don't need to figure out what is the, I mean, the whole problem is. You just figure out one step. If you can do that, you can repeat that concept for all the steps, right? So if I go back one step from ij, I can either reach, I mean, I was either at I minus 1j or I was at ij minus 1. From there, I reached ij. Both of these are possibilities, right? Both of these are possibilities. Now, the thing is, if both of these are possibilities, which one, I mean, should I have taken? So I don't know. Maybe I was at I minus 1j or ij minus 1. Yeah.
Sir, this have I think you jumbled it up. It should be I and j minus 1 in left hand side and I minus 1 j in right hand side.
Why?
Because we are reducing the row.
Oh, okay. Sorry.
We are on the same column and similarly in that thing.
Wait. So this is I, right? And this is I. So I moves in this direction. So I is over here. So it is in the same column, right? I is moving in this direction. That's what I started my discussion with. I is always, in this example, I is on x-axis, j is on y-axis, right? This is fine. No error is there. It's okay. Maybe you missed that part of the discussion. Anyways, so this is the, so okay. So finally, these are the 2 points where I can reach, I mean, where I was earlier in order to reach ij. Now, which one, I mean, which is the correct one? Which one of them was I mean, I was on which one of them? I don't know that.
No, it is, both are
Possibility. Possibilities.
possibilities.
Now, how to distinguish between them? Because our main concern is what? I need to find out total number of ways, right? So what is the next thing that I can do?
Use both ways.
All the pathways from 0 to I minus 1j and all the pathways from 0 to I j minus 1, you have to add 1 to both of them.
Exactly. So basically, I would write, let's say, number of path to reach I comma j is basically the number of path to reach, let's say, I minus 1 comma j, right? So this many path, or right?
What
And-
does P denote?
Sorry, p means the number of paths. So this p of I j minus 1 will store the value of number of path to reach I comma j. Okay, you need to have the count, right? I told you. So basically,
So
p
here
of
it should be added, no?
that
Not
I'm
one
com-
value will be there.
I'm coming to that after this discussion. It should be added. That's why I wrote or. What do we write? When I write or, it means addition. When we write and, it means multiplication in our normal sense, right? So that's what it means. So we'll come to that later. So p of 5 comma 10 is equal to what? It will store a value of 15 factorial by 5 factorial 10 factorial, right? So this is p means this thing. P of 510 will store this value. So let me just go down a little bit.
Sir, these cases are like we're discussing for no obstruction cases.
Sorry, there is a lot of noise from your side. I cannot hear what you are saying.
I was saying you are discussing about the no holes or no obstruction case, right?
Yeah, but I will come to the holes part. As you will see, that's the next, that's why I came to this slide. As you will see that in our analytical approach, having, I mean, whenever the holes were increasing, our approach was getting very, very tougher, right? It was, I mean, even increasing one hole would make the problem much more difficult to solve than the previous case. But here in this approach of programming, we will see that if I have these terms, right? That's why I wrote there or. P of ij would be P of I minus 1j, or P of, or means in the addition over here. So plus P of I comma j minus 1, right? From both of these possible cells, I can reach ij. So therefore, the number of ways to reach I minus 1j plus the number of reach from I to j minus ij minus 1 to reach ij. If I sum them up, that means that would give me the total number of ways to reach P of ij. So this is the total number of ways to reach P of ij. So that is the meaning of P of anything. So P of I comma j means the number of ways you can reach from 0, 0 to that P of ij. So this is one equation, the primary equation, right? Now the next thing is, so if this is the main primary equation or the recursive equation, I have to find the base cases, right? So what is the base case? Base case is always see how the recursion works. As you can see over here, the recursion is doing subtraction. So whenever subtraction is happening, you understand that I will go to the, at some point I will reach 0, right? So your base case will be something related to 0. So that is the base case. When if I'm subtracting in both these areas, so here also I'm subtracting in y coordinate and in x coordinate also I'm subtracting. So p 0, 0 is one possible base case. So that basically means when you are at the starting position of that cell, right? So here 0, 0. So if you are at 0, what does p 0, 0 means? The number of ways to reach 0, 0. So number of ways to reach 0, 0 is 1, right? So you are already there. So that means, I mean, one way is only there. So basically that particular way, I mean, that one way where you are present there. So that's why you write p 0, 0 is 1. Now the next can be that you might end up, I mean, so let's say I'm subtracting I minus 1, right? So I'm subtracting x coordinates. So I might end up in this area, right? Over here. So that is, no x is there, x is 0 and y is, I mean, I might be here, right? I might be here or I might be here. So in all these cases, I is 0. So I is 0 means I can have any term, something like 0, comma, some j value, which is, let's say, write it j. So any such point where 0, comma j is there. So that means how many ways I can reach my destination from 0, comma j?
Only one.
Are you sure? So let's take an example.
No, from 0,
From
1
0,
to
you can
3
reach
will
only
keep
one way, no,
increasing,
sir?
sir. Plus j, that will be j ways.
Okay, so let's say you are here, right? How many ways you can reach to this point?
Only one way, sir. We can go only up. You cannot go right. You just have to go up.
Is it so?
So what is the question?
If I want to, let's say, if I am here, how many ways? But what is the previous steps? Or let's say how many ways I can reach this point?
2 ways, sir.
Correct.
One way. That from 0, 0 you can go in only one way, no, sir.
Okay. So from here, from I mean, I can reach this point by I mean only by taking two up movements, right? Only one way is there. If I am here, then how many ways are there?
Again,
one
one
way,
way
one
only,
way.
sir.
Again one way. So any point on these axes
It's one way.
is always one way, right? All of these are all of these, whenever I need to reach any one of them, only one way is possible. So when I'm at any term like p of 0, comma j, or let's say the other way around, which is p of I, comma 0, right? So that would be essentially equal to what? That would be essentially equal to the number of ways you can reach to that point, which is 1. Now the one important point over here is that I mean, so basically you have 3 base cases, would be 1, sorry. P of 0, comma j would be 1. P of,
Why 0, 0, 1, sir? Why is P 0, 0, 1?
I mean, so if you write p 0, 0 as 0, then your base case wouldn't work. I mean, so implicitly it means that there is a one way you can reach 0, 0, and that is that way itself. If you write 0, 0 to be 0, since we will use this, I mean, implicitly it doesn't mean anything in that respect, but if you
No,
initialize,
sir. From 0, 0 to reach 0, 0, how many ways are there? There is only one way. That is the way.
that's what I'm saying. Only one way, and that is the way, that is you are present there. So that is the meaning behind it. But if you are feeling a little bit, I mean, what's counterintuitive sense over here? So let me tell you from a, I mean, Jugaad perspective, that if you make it 0, 0, I mean, the p 0, 0 as 0, so the initialization wouldn't work. I mean, because you have to sum up, right? So if you initialize with 0, then the summation wouldn't work. So that is from the Jugaad perspective, but the idea is, again, I mean, I don't find it that much counterintuitive. If you are at 0, 0, the number of ways to reach 0, 0 is only that way. That is, you are there, that particular way, right? So anyway, so you have these three base cases, and you can also modify these two cases. So this is the boiled down version of the cases, but this also works. If you write this also works, but it doesn't make any difference because at the end of the day, this will also boil down to one only. So, and this is the recursive case. Fine. So now we have found the recursive case and base case. Now one thing is left, which is the block, which was our main concern. If block is not there, then we don't even go for programming and all of that.
So, but why is the pi0 equal to 2? Or is it
Switch.
1?
Where is it 2? No, it's not 2, it's 1 only.
It's 1.
Okay, so the block part, see how much simplicity we'll get. I mean, how much simpler it gets when we use programming. The only thing for block is this. You don't have to take care of anything else. If there is a block, consider Pij to be 0. That's it. Okay, so now you have to simply write the program. I don't think the program is there. I think the program is part of your one of the practice assignment. So so basically you got one recursive statement and one block corresponding to block Pij is 0 and others are base cases, right? So now what you have to do is simply write a 2D program. Basically take a 2D array, two array. Basically take a 2D array, and in that 2D array you have to fill it up in this manner. How this is getting filled up? It is getting filled up because of the recursive statement and the base cases statement that we discussed earlier. So you use that to fill up a 2D array or matrix, whatever you want to call it, by following those induction rules. And obviously, since you are working on a 2D matrix, you need to run 2 loops, right? So just think of the 2 loops, how to write the conditions of those 2 loops. How will you write the condition of the 2 loop? Let me give you a hint. Whenever you are starting loops, right, we know that we are starting from the bottom up approach. We were told that we will be using dynamic programming. So always we will think of what is the prerequisite. So in this case, and in case of our all this problem, what the prerequisite is nothing but the base case, right? You have the base case, that's where the recursion ends, or if you go the other way, that's where the program starts. So wherever recursion ends, that is basically the base case. That is the base for your program, right? So if I go from bottom up approach, then that is the starting case. So you see what are your base cases. You start your loop from the base case, right? So in this case it is 0 0. So as you can understand, your base case loop would be starting from 0 0. So yeah, so start the loop from the base cases and go till the top. I mean I comma j or whatever it is, m comma n. So go till that point, okay? And in those 2 loops, in the loop body, I mean, what you have to write is you have to take this 2D matrix which is formed over here, and you need to put value to each of the cells of those 2D matrix, and that value would be it will be very simpler to put that values, because all you have to do is basically, I mean, use that equation, recursive equation which we got. P of ij is equal to P of that. P is basically the matrix which we are talking about. So P of ij equal to P of I minus 1j plus P of ij minus 1, right? So, and you follow this constant. Before doing that, you have to check if P of ij equal to block. Then you write P of ij equal to 0, else P of ij equal to P of ij minus 1 plus P of I minus 1j. And that's your basically the code. I anyway discuss the whole code then, right?
So IU run from 1 to I minus 1. IU run from 1 to I. Sorry, IU run from 2 to 6. And no, sorry, sir. IU run from 1 to the rightmost part.
What are you saying? I'm not getting. IU, what is IU?
I variable you run in the loops.
Yeah.
I variable you run from 1 to the 5.
Correct.
And J you run from 1 to 10.
Yeah.
And then you calculate, use the
recursive statement. Yeah.
Yes.
Right. What you have to do is simply run the loops as starting. See the base case. What is base case? Base case should be your 0 0. or in that sense it would, if you do the 0 0 part separately, all you can start it from 1 as well. So 1 to 5 or 1 to 10, you can do that. After that, what will you do? First thing is your initialization. What is initialization? These areas, right? So basically your for I in range, let's say this is 10,
1
right?
to 6, 1 to 6.
Right, your P of
1 to 6, no, sir.
I am doing the out top one. Let's first initialization has to be done on this part. So I'm doing for I in range 10. What you have to do is your
I in range is 6, sir.
okay, fine. I mean, I'm taking one variable
Take it either way, but yeah.
for j in range 10. All you need to do is first your I would be 0 uh, and your j would be j would be
Equal
equal
to
to
1.
Writing
Equal
the
to 1.
code for this, and the code is not even in the slides.
Okay, that is important. Right, right.
5, right? But how many? No, 6, 1, 2, 3, 4, 5. Yeah. Right. After this, you will write two for loops. I equal to 1 to uh, your 10. Sorry, your 5.
5.
And here you will write for j equal to
1 to 10.
10. At first, we'll check if your p of I comma j not equal to some. Suppose the blocks are indicated by -1 or something, right? If it is the case, then p of I comma j is equal to the recursive statement whatever you had. That's it. Fine. There would be some fine tuning required, but this is basically the core part of the code.
Pij not equal to -1. Why, sir?
I mean, you need some way to indicate the block, right?
Okay.
This is corresponding to block,
Okay, block. Okay, block.
right?
Yes.
And or let's say if I think the p of ij was indicated with 0, right? Block was indicated with 0.
Yes, 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 yes.
So yeah, 0. Fine. Is equal to 0. Suppose. And let's say here at some point before starting the code, you initialized all the blocks to be 0 if I comma j is block. This might be given as an input to your program, right? It would be given that these cells are blocks, so please assign them to be 0. So simply at first, I mean, assign those cells to be 0 explicitly one by one manually. Now once you do that, after that you start the code. Okay.
So block will be indicated by some other number in that case.
And it depends on that. I mean, small things, right? You can adjust that. Some implementation it might give, it might not give. You can do. It's fine. Fine. Okay. So this is the whole discussion. Now, as I've already discussed the code, but I will delete it now. So what's important over here is how to think of the code of a dynamic programming. The thing is very simple. Whenever you are trying to solve any dynamic programming, you have to first find out two things, right? So let's say this is the, let me come back to this point. So while solving dynamic programming, the approach that we do is this. At first step one would be that find recursive relation, right? Your step 2 would be find base cases. Step 3 would be use the base cases, use the base case conditions or relations to understand where the loop should start, or let's say what should be the loop initialization. And fourth part would be basically your
Sir, for what are these steps? I mean, what is this thing?
you are not audible properly, right? So here is stuff. I cannot hear you.
I'm asking that for what these steps are you writing?
To write a dynamic programming to any
Okay,
to
okay. That was I was asking.
yeah.
It is a heading.
Yeah. Okay, so this is the, let's say these are the four primary steps. The first is find the recursive relation. Second is find the base case relation. Now use the base case relation to understand what should be a loop initialization. So the loop starts with the base case values, right? So you got the loop initialization. Now once you got the loop initialization, next is the body of the loop, right? So what to write in that? So in that body you will write the recursive relation, because the recursive relation basically calculates the values at each position, at each iteration of the loop. So you write that recursive relation to calculate the values at each position of the loop, and if there are some other particular constants which are specific to the problem, you use those constants inside the loop variable. Sorry, inside the loop body. Okay, so these are the primary four steps to write a program, dynamic programming, right? How to think of it. So if I just go back to our discussion and let's say tally this out, then what did we do over here? We at first found out these uh, base cases and recursive relation, right? Now this recursive relation, I used it inside our if statement, remember? So, and initially use the base cases to figure out where should the loop start, and the initialization was also done because of the base cases, right? So we had these two 1 1 1 initialization which we did using the base two loops, right? So the base cases are used for this initialization purpose, and recursive case will calculate the value of the basically each value of the array cells, of the matrix cells, right, inside the loop body. So this is how the basic structure, a general structure of a dynamic programming looks like, and those steps are basically the general steps to solve a dynamic programming question. By the way, these values are filled up by, as you can see, these values are filled up depending upon those recursive relation and all those statements, basically the code that I wrote over here. So that is one example, which is the grid path, right? The code is not given over here. I think that's for you to solve, but anyway, I discussed it. Now, as you can see here, it becomes very easy. I don't have to care about how many holes are there, as long as I have this iteration, I mean initialization of all the holes to be p of 0. I mean p of I comma j would be 0 if there is a hole at I comma j. So simply assigning one of, I mean just this statement, writing this statement takes care of all the complexity when multiple holes are there, right? Okay.
Sir, can I ask?
Yeah.
What if in a question we are given that we cannot pass the rules, but we can jump it. So will it be the same case?
Jump it.
Yes. Means we
Jump
can,
means
if there are multiple blockages, then we cannot jump. But if there is only one block, we can jump obstruction.
okay. So let's say, what do you mean by jump? Does it mean, let's say, if I have a jump over, if I have a block over here,
Yeah.
then, and let's say I was initially present at this position. This is my current position. Now, if I have a block over here, then what do you mean by that? If I want to make a right movement, so where will right movement take me? To this
Right.
point?
Yes.
You mean this?
Yes.
Okay. So then the equations will change definitely, because if I get p of ij equal to I mean zero, I mean not zero. Let's say basically if ij has a hole, then even if I write this, then that means that I have a way to reach this point by jumping. Maybe I can reach this area by some jump. So it will change.
So, so how can we change according to this condition?
With that would depend on the implementation. What do you want? Okay,
Okay. Actually,
fine.
there was a question in practice assignment related to this. I just asked. Okay.
You have to think it. That's why, I mean, there are a little bit differences. You can might not also want to change it if this. So that's what I'm saying. That you have to be very specific about the question and what do you want. Then only we can think about that. So, but let's discuss one other important point now. So this is a pretty unique example to, let's say, contrast the benefit of memoization and dynamic programming. So let's say these are the blocks that I have. Fine. Now, if I want to use the memoization approach, that is the top-down approach or the recursion approach, right? So how will I write my code? I will directly start from recursion happens from top-down, right? So you f of 5 comma 10, this is how the program starts. And then to reach 5 comma 10, I can go to two possible path, which is basically f of 4 comma 10 or f of 5 comma 9. These two options are there, right? So which basically means I can recursion will go to this point or to this point, right? After that recursion from this point, which is what 4 comma 10, right? From 4 comma 10 I can go to this point basically. So as you can see 4 comma 10 I can go for f of 3 comma 10 or your f of 4 comma 9. But as you can see 4 comma 9 has a hole over here, so this part is not possible, so this remove it. Okay, fine. Now from f of 3 comma 10, what are the positions that I can go to? I can go to either f of 2 comma 10 or either other way f of 3 comma 9. 3 comma 9 is again not possible, so you remove 3 comma 9. So 2 comma 10. Likewise, if I go in this direction, right, all I can think of is I will either go for 4 comma 9 or f of 5 comma 8. So what is 4 comma 9? 1 2 3 4 and 9 is over here. So this is your oh wait, did I make a mistake over here? Left 4, right? 4 5 is 5 comma 9. Okay, 4 comma 9 is okay. Yeah, this point. Now 4 comma 9 is not possible because 4 comma 9 is a hole. So for 5 comma 8. So as you can see over here, now this will grow linearly, just like this side was growing linearly. This will also grow linearly. I will get f of 5 comma 7, f of 5 comma 6, and likewise. And here I will get f of 1 comma 10, likewise, right? So you see the beauty over here is I am basically finding the path. If you see these coordinates, I'm basically finding the path like this or the other way, like this. I'm not going in the part, I'm not going inside this part. These cells will never come in the function call. So basically, what I mean is I will never encounter a function call like this. Let's say this point. What is this? 2 comma 1 2 3 4 5 6. So this function call will never be encountered in these iterations. I mean in this recursive statement or recursive call stack. I will never encounter f2 comma 6 or anything which is in that yellow part. Right? So that means this is reducing the number of function calls which is there. But if I use iteration, right? So iteration starts from bottom up approach. So in that kind of scenario, what will happen? Let us see. So we will start from here, bottom up. If I start from here, I will go in which manner? I mean, I will grow in this direction only. So I will consider all these internal spaces. I will go like this, maybe like this, and then so I will do something like that. So I will consider all these internal spaces in action, right? But whatever I use, right? So till this point, wait just a minute. So whatever values I use, to reach these cells, right? All these cells which I am now highlighting. If I did all the calculation in this part of the graph to reach all these cells, but then I saw that there is a blockage like this. So the computation that I did till now to reach all these cells, basically these cells,
You say in this case, memoization is better, right?
yeah. So the calculation done to reach all this yellow highlighted space is basically it is going down into vein. Why? Because you have blockage after this. So you cannot use the path that you have calculated till now. So the path which went along this area, right? Like this it was going. So only these two paths can take us to the destination. But your
Actually, we said that dynamic programming is more efficient in terms of the system time than memoization, but
correct.
that is not always the case.
Yeah, in this case, so that's the point, that's what I'm raising over here. So as you can see, this is a particular use case where bottom up approach wouldn't work properly and top down approach works better, right? So use case dependent scenarios always, that's what I said, that use case when there is a particular scenario, in that case recursion or memoization will work nicely, like in this particular example. But in general, recursion is a system heavy work to do, and that's why we prevent it. Okay, but point of putting up this example over here is that it's not always that recursion works bad, right? The thing is, if the problem statement is a tricky one which suits the properties of recursion, which is basically the top down approach, and along with that, let's say yeah, so in that kind of scenario we can use memoization rather than dynamic programming.
So one thing is here, when you say trick, so our target was 0, 0. If we change our question to target was, let's say 1, 2, which is in the yellow zone. Any point in the yellow zone is our
Correct.
target.
Then
Right?
then it would be a problem. Then again, dynamic programming would be a better work.
Can we do both simultaneously?
Yeah.
Top to
Yeah.
bottom and bottom to top.
Well, what is the
side by
need for doing that? You are basically solving the same problem in two different approaches. I mean, you can do that as a hobby exercise, but certainly not as a part of the fundamental algorithm, or let's say, yeah, that's the idea. Fine. So this is your.
Sir, suppose we want to go to 3.8. Suppose we want to go to 3.8.
Okay.
3.8. Then memoization won't work, right, sir?
Memoization won't work in the sense that it would work in a different manner. You have to add boundary conditions. You have to think about what should be the proper base cases. So you have to think about that. You have basically make changes in the code, right? Okay. So now we will go to the. So as we have a flavor of this, how the dynamic programming. Basically, we will take one and we figure out what was the previous step, and then from that previous step, we will try to find out. What are the base cases, what is the recursive statement, and that's it. So in all this dynamic programming example that we will see now, the first two steps, figuring out the base case and figuring out the recursive statement, these two are the most important point. Once you have figured that out, your code is done, because the base cases will tell you what should the loops look like, the recursive case will tell you what should the loop body look like, and that's it. In all the dynamic programming question, you will have two loops and you will have a loop body. That's all you have to think about. Okay. So figuring out the recursive statement and figuring out the base statement or base cases are the most important things to be done in dynamic programming. Now let's go to another example. This is the longest common subword or longest common subsequence example. Now what do we mean by a subword? Subword is nothing but a substring. Okay. So like as you can see over here, bisect, right? So in this case, SSCT sect is there and SSCT sect is there. So sect is a subword or substring, whatever you want to call it, and sect is common between both trisect and bisect, right? So we will try to, given two such strings, right? I will try to find out what is the longest common substring within those two strings. So you have to find a common substring which should be longest. So there can be multiple substring between two strings, right? So multiple possible substrings can be there. So multiple possible common substrings, I mean. So what do I mean by that? So let's take an example. Now, as you can see in this example, let's take this part. Right? So this is a common subword. Again, if you see this part, this is also a common subword, right? Again, actually, this one is a common subword, so to say. Right? Anything else? Single element you can consider as one trivial
ACC,
subword.
sir. ACC.
ACC. ACC is anyway part of this larger word, right? Okay. So I don't have anything new. So as you can see, there are three subwords, so to say. So there one A and this is a one length subword. Then over here one, two, three, four, five length subword, and this is 1, 2, 3, 4, 5, 6, 7 length subword. So there can be multiple subwords within two words given to you, and I want to find the longest word within them, longest subword within them. That's the question statement. So how to approach it? Any ideas?
A quiz to question.
That depends.
Means we have to just scan each and every element, and wherever they differ at index, we have to stop.
Nice. So what we will do is we'll scan each and every element, and wherever they differs, I will. I mean, basically that's basically a failure of your operation, right? So that's where you have to stop. So how much time will that process take? Anyone?
Length of the first word multiply by length of second word.
Nice. But anything you are missing? Let's say the length of the first word is x and the length of the second word is y. So will the answer be x into y?
So what have you asked?
What I mean is that let's say I have I mean, so length. I have two words, right? And I want to find the common subword between them, right? Longest common subword, whichever is the longest. So how to think of it? How can I find it? So if I do that simply by checking each and every position, I check that if this is common, right? So let's take an example. So let's say uh, this bicep one only. Okay, let's take this example only, which I wrote. What I can do is I can be at A and I can check whether this A is equal to this A. And okay, I got it. It is similar. Next, I will check that, okay, if the next A is equal to this C. So you see that, no, it's not similar. So if I consider my subword which started from this first position, but then I say that this AA is not equal to AC, so the subword cannot start from, I mean, cannot be AA, I mean, cannot be too little low. So next thing that I do is now I start my checking. Let's say now I start my checking from this C and here at A. Right? So from C I check if C is equal to A, no, C is not equal to A. Okay, so I will shift forward. So this is what I mean. So basically what we are doing is, in order to check for common subwords between the two strings, we have to check every possible starting position among these two strings, and then we have to check till how much is this match happening of the subword. So let's say if this string is x length long and this string is y length long, then I need to search for, I will be at x into y number of positions, right? Starting, let's say starting positions. And in each of this case, let's say, I want to, in each of this case, I want to find a substring which would be, let's say, at most of y length, because y is, let's say y is the smaller length string. Okay, it might not be that, but I'm just, which one is smaller? Okay, suppose y is smaller. Okay, I don't know, but if y is smaller, whichever is smaller, then I will have that as the maximum length of the substring possible. So that can be there,
Into y.
right? Provided when x is greater than y. So in that case, therefore, it will be x into y square. This much time would be taken by you to find a common substring between these two strings, right? But we have to solve it. How to, do it in a better time. So this is the brute force approach. How do we write it? Simply using multiple loops and if condition.
Sir, we can choose the minimum of the string, right? And run the loop only till there.
That is fine, but that also would take an x into y square amount of time. Why? Because you have x into y number of starting point.
Okay.
Okay, fine. So how to solve it using our DP concept? Okay, so you see that as I told you, in any DP problem, what we have to figure out is what is the recursive statement, what is the base condition, and then we can figure. That's our work is done. Mostly the work is done. So now let's discuss that how can we think of the recursive statements. So as you can see that in our previous discussion of grade, when we are at ij, we were thinking what was just the previous step, either I-1j or ij-1. Any of these two can serve as the previous step for me reaching at ij, right? So that was the point. Here also we'll see what is just the previous step. So in all the questions that we will discuss from now, right, we will always consider that our string scanning starts from this part, from the back part to the start. Normally when we do, check or compare between two strings, what do? We start from the left hand side and compare one by one and go towards the right hand side, right? But in all this discussion, we'll start from the right hand side and go to the left hand side. This is the point of discussion. So that means if you want the value of, or want to work with that ith position, you must always be aware of I-1th, I+1th position, because I+1 is over here, right? So if you know the value of ai+1, then you will only get the value of a of I, because a of I+1 will be used in getting the value of a of I. Okay. So now we will write the recursive statement. So let's say these are the two strings which has been given to us, ai to a-1 and bj to bjn-1. Basically, these are simple two strings are there. Like the example that we wrote just before, like that we have two strings. And the first thing is when both of them are not equal. A of I is not equal to B of J. So in our example, right, suppose this is my V, this is my U. Fine. Now let's say I start checking from this point, and let's say basically, yeah, I will check AC. This V, this first C is equal to A or not. So if it is not equal, if this is not equal, as you can see, then the LCW of IJ would be 0. Now what does LCW of IJ mean? So in last case we saw P of IJ, right? P of IJ basically is the number of ways to reach I comma j from 0, 0. That was P of IJ. In this case, LCW of IJ means the basically the matrix I comma j cell, which will store the length of the longest common subword between I comma j. So when I write LCW of I comma j, that means this v and u, there are two strings, and within those two strings, I want to check what is the common subword till the ith position in v and jth position in u, right? So that's what we want to. So LCW of ij, if it is not equal, that means I mean, is there a subword at I comma j? So you see that the I comma j entries itself doesn't match. That means the subword is not there. Therefore, subword discount is 0. Now, if there is an equality, that means LCW of ij, I mean, ai and bj are same, right? So that means what? I am at my current comparison of this number, these values, right? So let's take this part for better clarity. Let's say when I am at this position. I am at this position for A and I am at this position for this thing. Okay. Now, as you can see, this AA matches. So this means AI BJ matches, right? So all the terms over here, let's say these are your, let's say these are your AI and these are your BJ. Fine. So I check this, put this C and check this AA is matching. Okay, fine. What is the next step? Just let's say just the previous step. In order to reach here, I told you we will always proceed from right hand side, right? So that's why LCW of I plus 1 j plus 1 plus 1, right? Because the thing is we need to find the maximum length of the common subword. So if these two matches, that means whatever subword was there, longest subword was there in this blue part. I don't know whatever long it was. I don't want to know also. But whatever was the longest common subword in among these two blue areas or blue marked areas, I will add 1 with them, because why 1? Corresponding to this A. Corresponding to this A, I will add 1 with them. So 1 plus LCW of I plus 1 j plus 1 is equal to LCW of ij. Right? This 1 is because the subword length got increased by 1, right? Corresponding to the addition of this A. Fine. So whatever was the common subword in I plus 1 j plus 1, with that I add 1. So that means LCW of ij equal to 1 plus LCW I plus 1 j plus 1. And now as you can see that the recursive case is growing in a plus fashion. In the previous case, recursion was happening in a minus fashion. Here it is happening in a plus fashion, and that's why the base case would be what? I am since adding, so I can grow up. In previous case it was subtracting. That's why it meant I can go down to 0. Here it is addition. So that means I can grow up to be, M or N, either one of them, depending upon the length of U is M and the length of V is N, whatever it is. That's how that would be the base case. So that's why LCW of M comma N is one base case, and I comma N is also another base case. Although both of them would have the same value 0 0, but both of them are separate and they have their own reason own base case. Got the point? Hello.
So we are going from left to right, right?
Right to left. Right to left.
Why? Because like we are increasing I plus 1, j plus 1, right?
Yeah, so that means what? In order to calculate ij, I need the value of I plus 1, j plus 1. So I plus j plus 1 is already been calculated, then only I can use it to calculate ij.
Okay.
What about MJ, sir? LCW MJ?
LCW of?
MJ.
Oh, that is the next term, right? LCW of this. So your M comma j, right? Same thing.
That is also 0.
Yeah. Fine.
Because there is no such index as M. That's why.
No, index is there. I think that is not mentioned, but it should be there. Oh, it is in the next slide.
Because the index will be from 0 to M minus 1, right?
No, here the index we are keeping it one more. The reason for that is you will see when it is not that much of a difficult situation, but basically to make things simpler, we are keeping it. Okay, we are basically creating a 2D matrix of M plus 1 N plus 1 size, not an M cross N. It is M plus 1 cross N cross 1 size matrix. Why we are making it, we will come to that. It is simple. No conceptual thing is there, just to make things look good. But the main part is this: if I have a substring at some point, that means whatever common largest substring I had earlier to that point plus one corresponding to this one, which I just added. So that's why LCW of I plus 1 j plus 1 plus 1. Okay, does it make sense? So let me just, in this manner, let me again state it. So if I want to find the largest common substring and there is a match at this point, both of these A matches, all I need to do now is I will add. So the LCW of this is I, and let's say which one was I? This is I, and this is J. So LCW of I comma J means I need to find the common substring, largest common substring, or the let's say the size of the largest common substring between the when u is running at I and v is running at J. Within these two positions, I need to find the value of the length of the longest common substring. That's our question. So LCW of I comma J stores that. LCW of I comma J means the longest common substring between when v is at J and u is at I. Now, how to calculate that? I will simply write it as LCW of I plus 1 j plus 1 plus 1, which means that whatever was the common substring, largest common substring in the earlier part, in this part, I don't know what it is, but whatever it was, right? So the length of that would be stored in LCW I plus 1 j plus 1. With that, I am adding 1. Why I am adding 1? Because this A corresponds to the addition of that 1, right? Because in the next, so now I have the longest common subword as whatever I had in this yellow part plus one more, which is basically corresponding to this same A which I found. Okay, so these are the recursive statement. This is the recursive statement. These are the base case statement. And again, since you now figured out the base case, you know the loop will start from, since you see that here the base case can grow up to m comma n, and it was initially starting from 0, so you can start from 0, go till m comma n, and use the recursive relation to put the value. So you will see the code now. By the way, before going to the code, as you said that why we are adding, one more extra cell, that is basically our arrays look like m plus 1 cross n cross 1 matrices. Why this m plus 1 and cross 1 is required? This is basically because we want to create it in this manner, because it looks, so here I start from 0, 1, 2, 3, 4, 5, here also 0, 1, 2, 3, 4, 5, and then I have this area which indicates the termination of our code, right? So where basically one of the initialization is this, that my term ends, so I have to have a base case, right? At some point I have to end the work. So that is basically this sixth cell. If I reach this, if it crosses the size, then I have to terminate it, right? So that's where we do the termination, where it crosses the size. So that's why the table is m plus 1 cross n cross 1 matrix. Fine. So how will we fill up this? So we have, first condition is if AI is equal to Bj, right? So then if I have this AI equal to Bj, so all I need to do is I will add, right? Because I got one more character common. So whatever was the length of, in this case, LCS, longest common substring of I comma j would be equal to longest common substring, but whatever it was in I plus 1, comma j plus 1. Whatever was the longest common substring in this area plus 1. This one is corresponding to the common character that I just found. So this is one recursive statement. If it is not equal, then it is simply 0. And the base cases we already discussed, right? Fine. So now what to do? Let us see. Yeah. So as the base cases were already, we have discussed, those were 0. So all these would be 0. Right? These are all zeros, as you can see. And after that, we'll simply use the recursive statement to fill up. So let's say this t and this t are same, right? If they are same, what will we do? LCW of I plus 1, j plus 1 plus 1. So LCW of, sorry, LCS of I plus 1, j plus 1 plus 1. So basically this I plus 1, j plus 1 plus 1 makes it 1. Okay. Now when I will be at this position, is it same or is it different? C is there, E is there. It is not equal. Right? So if it is not equal, then 0. Likewise, I have to fill up.
So you'll go from the outer loop will go from 5 to 0, and the inner loop will also go from 5 to 0.
Outer loop will go from 5 to 0. Why?
So 2 loops will we have to run to fill the matrix.
Acha, acha. Okay. So in the code part, yeah, correct, correct.
So either you can, do you have to go with columns or you can go with rows also?
Whatever, yeah. So that's it. I mean, there is nothing else to discuss.
But
Basically,
the outer loop will be that of the smaller word, right?
that depends again on your implementation. Yeah,
Doesn't
make any difference.
You can use either, I think.
Yeah, doesn't make any difference. It will anyway work out. Okay, so I'm not filling this whole table up because it's basically using those recurrence relation just to fill up this table, nothing else. Let's go to the code a little bit. Implementation. As you can see here, this is the array creation part. These things are fine. This is the main part of the code. Okay, so 2 loops, simple 2 loops for C in range, for R in range, right? And we are, as you can see, we are starting -1, -1 is this. So we are starting from the bottommost right corner. From there we are starting. So if, well, U and V are basically the 2 strings. If U of C and U of R and V of C, this IJ, basically this U, C and R are basically corresponding to your I and J concept. So if U of R equal to V of C, that means there is a match. So AI equal to BJ, equivalent to AI equal to BJ. So if AI equal to BJ, then this is LCW of RC equal to 1 plus LCW R plus 1 C plus 1. Or else if it is not, then LCW of RC equal to 0. That's it. That is the base case, and the base case helps you to come up with this. Recursive case helps you to come up with this.
So here it is giving the size of the maximum word.
Correct,
But
correct.
how can you recover the actual subwords?
Yeah, so in order to recover the actual subword, you have to add one extra line of code in this whole thing. That what is that line of code? If wherever you are, I mean, so your subword is only getting formed.
If statement like UR equal V, we can add a line there, right?
Yeah, exactly. So that's what I wanted to say. So whenever you are actually adding one character to your subword, that is happening in that if statement, right? This if statement is the place where you are basically adding every time a character into your word. So whenever you are adding this character, this equality is helping. I mean, equality is true. Here you need to write one statement where you basically append each of the characters that you encounter into a list. And basically at the end of the iteration of all this, I mean, of this algorithm, whatever is present in that list is basically the longest common subword.
But that will be in reverse. You have to, you have to.
Yeah, that will be in reverse position. You can just make a reverse and then print it.
Okay.
So you have to just add one line here, and that line would be simple. Let's say L dot append U of R. That's it. Okay. So as you can see, the dynamic programming is very simple to code because all the program looks like this. You have 2 loops and then you have a loop body.
No, sir, but we can have multiple subwords in a single. So every time this will work, it will not give the right answer because you may have multiple subwords.
So in that kind of scenario, basically, since here what we are doing is, here the LCW of RC greater than this condition is held. See this, that if LCW of RC is greater than max CLW, we are having this max property. then max LW, LCW of RC. This is what we are doing. And at the end of the day,
Once you
we
get the max, then you have to go reverse it, I think.
yeah, that's what I'm meaning. So if you want to print the word, right, print the max word, then you have to add another condition. So regarding this max property. So here we are only worried about the what is the maximum length. So that's why I'm keeping track of just the length. Okay, so if you want the max word, I mean, what is that max word? Then correspondingly, you have to keep track of what are the words, and whenever it is max, you print that only. Fine. So how to do that? If you want to think about it, how to do that? So how are we keeping track of this max? I mean, there can be subword is fine, but what is the maximum length subword, right? So if I want to find that, how are we doing it? So once you have got this LCW of RC equal to 0, after that we look that LCW of RC is greater than max that we have found till now. Now if it is greater than max, then we change the max to be LCW of RC. So whenever this condition happens, then only you print. Otherwise you don't go ahead. So that will take care of that max property is being counted. Or let's say whenever this condition happens, you can proceed with the list which you have, I mean, the appended list which you have formed for the substring. If this condition fails, right, so then you can simply clear the list, whatever is present, because that would correspond to another shorter length substring. So there are many ways, I mean, that I leave it to you how you want to do it. Okay, so now as you can see, the time complexity over here is simply m into n, because you have two loops and everything that's happening within this is basically constant time work. So this is m into n time operation. But initially we needed m into n square time of operation, right? In normal brute force approach. Fine. So now we will come to another next topic, which is basically a little bit different, which is the longest common subsequence. Now, what is the difference between a substring and a subsequence? So, substring is a continuous, let's say it is continuous part. So, as I told you that in your bisect and secret, as you can see, SEC is there.
Shall
Which is
we discuss the brute force approach, right?
no dynamic programming, right?
Okay.
Right. So why the brute force? This is using loop, right? We are starting from the base case.
About the OMN square complexity. So how
That I discussed, right? There are m into n starting position. Just check the initial part of the live session on, in the recording. Okay. So what is subsequence now? Subsequence can be discontinuous. So substring or subword must be continuous, right? So in this example of bisect and secret, suppose, right? So SEC is a continuous part, SEC. So if I ask you what is the longest substring, tell me what is the longest substring.
SEC.
Correct. So longest substring is SEC, which is basically equal to 3 length. But if I ask you which is the longest subsequence, then that is sect.
SECT, okay.
Why? Because see, after this SECT is occurring, and after this SECT is occurring at last, there are some elements in the middle, but I don't need to worry about them. As long as the relative order of the characters are held in both the strings, I will consider that as a subsequence. Okay, it might not be continuous. There might be gap like this between them, but I will still consider that as a subsequence. What the point? What is the difference between substring and subsequence? Substring needs to be continuous. It cannot have a break in between. Subsequences can have break in between as long as the character order, relative order of the characters of the word remains same. So that's why I'm considering these two T's which are not continuously located. It is far apart. So this is done. Now what is Now, once we have understood the subsequence, what are subsequences? Now, again, in order to write dynamic programming, we have to find the recursive equation and the base cases, right? So let's go to that. So where is it? Fine. So the thing is, in longest common word, what was the concern that, let's say, longest common word, I'm LCW I'm writing. When I'm at I comma j, it meant the longest common word between the positions when I is running on u and it is at some position, and j is running on v and it is at some position. So the longest common word between these two positions, whatever is the length of that word, would be stored here, right? Again, this is the same for longest common subsequence as well. Common subsequence I comma j, same concept, everything is same. Now it is just subsequence. Now, what would be the changes in the recursive and the base cases? First of all, let's take the recursive case. In the recursive case, if there is a match, right, ai equal to bj, then what we are doing, we are doing LCW of I plus 1, j plus 1, plus 1, right? Because this one was because of that substring character, common character that I just got. Now, in case of this else longest common subsequence, the same thing will happen, because again here also the same constraints are there. If there is a match, so whatever was the subsequence before that, longest subsequence before that, with that I will add 1 corresponding to the common character which I am just encountering. So the same things happen. Longest common subsequence I plus 1, j plus 1, plus 1. The thing that changes is with LCW of when I and j are not equal. So these both of them is with a of I is equal to b of j. But when it is not, a of I is not equal to b of j, then in case of LCW of word, I wrote I comma j to be 0. Right? So because there is no match in the character, so that at that position there is no subword, so it should be 0. But in case of longest common subsequence, since we don't care about the exact value, I mean exact positional value, the relative order works. Because even if there is a gap between the characters, common characters, I will still consider that. So therefore, LCW of I comma j in such a situation is not 0. It is something else. Now, what is it? I mean, what should we write over here? So the main idea over here is that when there is a mismatch between AI and BJ, how would it look? Let's say I have some AI over here, and let's say AI minus 1 and dot dot dot. And here I have BJ over here and BJ minus 1 and dot dot dot. Something like this. Fine. And when AI and BJ doesn't match, so this is a scenario when AI and BJ is not matching. Suppose A is something, B is something. These are two not matching. Now in substring or subword, I knew the positional value was important, but in subsequence, the relative order is important. So I can still have AI somewhere over here, starting from bj minus 1. Maybe AI is equal to bj minus 3, which is at some point over here. So A can match with any characters in this whole space. AI can match. Correct. So, or other way, this is a AI matching over here. Other way, bj minus 1 can match with any of the characters over here. That is also there, because now I am allowing discontinuance. Initially, continuity was there, and that's why LCW of ij was 0. But now I am allowing you to go out and reach other values. If there is a presence, then you can report it. So therefore, subsequence LCW of ij, there are two possibilities. Either this commonality can be there or this commonality can be there. So therefore, I will compare like whichever is the minimum. Either I plus 1 j or LCW of LCS of I j plus 1. Okay, so max, sorry, this is max, right? I want to find the maximum length. Whichever is maximum, that one I have to take. So this is the difference in case of LCD, longest common word and longest common subsequence. Any doubt in this? By the way, base cases again would be similar, just like the longest common word base cases. No doubt, right?
Yes, sir. There is a question, graded question related to this, with asking a decreasing length of longest decreasing sequence of numbers in a given sequence. So I tried this approach which was given here, but I could not decipher the the sequence. I could do the dynamic programming, but I could not decipher the actual sequence using the matrix, M/n matrix.
Sequence means I didn't get it.
Once you construct the matrix, then you have to give the sequence which is the longest sequence, right? Actual sequence.
Yeah, you have to return. Okay, if you want to return the actual sequence, then you have to just take care of the part where the maximum is happening, and then store the sequence in a list only in those situations where the max is. I mean the max is
The
hold.
approach which I used, it passed the
Cases.
public test cases, but did not pass the private test cases.
Yeah, so then that you have to think what case you are missing. That's for every problem, right? So you have to think about it. Maybe post it on discourse or discuss, right?
Because it is a graded question, I did not do that.
You can, you in graded question you are not allowed to post code or anything, but certainly you can post your doubt or discuss. That is fine. Posting doubt is okay. Okay, fine. So again, these are the two equations that we got, and simply by following these two equations, you can figure it out. So I wrote the longest common word and longest common subsequence in both the cases. This is the difference. In a longest common word and subsequence, the difference, when it is equal, there is no difference. But whenever there is they are not equal, then there is a difference. In this case, it is 0. In this case, it is the max of either one of them. And this case is happening mainly due to the fact of discontinuance. So I'm allowing you to have a break in the middle. Okay, allowed. Okay, so again, filling the matrix is something very easy to do. All you have to do is simply take the recursive cases and think about it. Just apply it. So all of this initialized to be 0. All of these are initialized to 0. And then what was the recursive case to calculate the values? The recursive case was 1. If the values matches, I will add 1 plus the diagonal term. So 1 plus LCW of I, LCS of I plus 1 j plus 1. If AI equal to bj, or if AI is not equal to bj, then I will take the one, either this or this, whichever one of them is minimum, maximum. That one I will take. Right? I will put. So what should be here? Let us write it here. All of this will be 0 anyways. So what should I write over here? Either if it is matching. So T is here and R is here. So T and R doesn't match. So it is not matching. So therefore, I can take either max of this or this. So 1. Okay. What should I write over here? C is here, R is here. So it's not matching. So since it's not matching, again, one of them over here. Max. Here E and R not matching, right? So since it is not matching, since it is not matching, maximum length I will take 2. Here it is S and R not matching, maximum length I will take 2. I and R not matching, maximum length I will take 2. B and R not matching, maximum length that I will get is 2. So then T and C is there, it's not matching, maximum length is 1. Then CNC is there. So I got a CNC, so that is a match. So once there is a match, therefore the AI plus 1, J plus 1 we add, right? So this 1 plus 1, which is 2. Then E and C to S and C to I and C to B and C to this I and C to where is this E? Okay, this we have to figure out. This 2T is there, so 1 and 0. Maximum is 1. C and E maximum is 2. Now again one E and E I got. So since there is a E and E, both are matched. Yeah, so this plus 1, which is 3. So I will not fill up this whole thing. So that's it. Again, you go to the code, same structure, everything same, nothing differs. Just the condition changes. Acha, one important point I forgot to mention. So over here, fine. So you have to check. Let's say only one cell is left. So let me complete it anyway. So E and S is there. So max. Here I and E is there. Max. B and E is there. Max. Here I have 1 and 0. T and S. So max. C and S. So max. E and S. So max. Wait. 3 to C and S, right? So max
4.
is 4 and IS is 4.
4.
Yes, is 4. Now, if I next thing that I want to do now is I need to find the string which is there.
That is the question, sir.
Yeah. So I need to find the string. So how to find the string? There can be even one point is I can have multiple strings which are common, which are of equal length, and that is the longest length. So let's say the longest common subsequence that I have is, let's say, 5 length. Now a 5 length is the longest common subsequence. That is fine, but there can be multiple such 5 lengths longest common subsequence. The longest, because none of them are smaller. There is no one which is larger than them, no substring which is larger, subsequence which is larger than, longer than them, but there can be multiple such same length subsequence. Okay, now how to figure that out? How to find the subsequences? See, subsequences are getting found whenever there is equality, right? Just like substring, it is already I told you to put a code at a particular position in the substring code, right? Where was that position? When that if condition was getting satisfied, when u of r was equal to v of c, right? That condition was there. So that means whenever ai is equal to bj is getting satisfied, that's the point I'm adding something, adding a character to be in my substring or in my subsequence. So I will only do that when there is an equality satisfaction, right? Whenever your basically ai is equal to bj, that condition is holding. So in this example of subsequence, where whenever this ai equal to bj is happening, so at that point, what am I doing? I am doing 1 plus LCW LCS of I plus 1 j plus 1, right? So whenever I am doing LCW of I plus 1 j plus 1, right, at that point our subsequence is getting formed. So I need to figure out all the position where LCW of I plus 1 j plus 1 was the, basically the operation that I did. So let's figure that out. So let's start from the bottom. So here 1 was there. I got over here 1, right? And here also it is 1. So where did it first equality get satisfied? Here TT was there, right? And here I got 1. Why? Because this 0 plus 1 happened. So this is the first point of equality. Then where did the next equality happen? Here, right? So I can go in this direction. And this is one equality. Right? And then again, where equality happened? This is one equal, right? So this E. Then Where did any other equality happen? Again, this SS is equal. So this is also equality.
Sir, equality happened here also, na, in fourth column and third row.
Correct.
Fourth column and third row.
Where?
Fourth column and third row.
1, 2, 3, fourth column.
Column number 4 and row number 3.
Here, right? Okay, yeah. So now, so this is one path. That's what I said. There can be multiple paths. So this is one thing. And again, from here, I can go to the top like this. And here again, equality is there, E and E. So,
But how, like,
right? This is one equality. We will come to everything. Just now, as of now, we are just checking the equality wherever it is happening, right? So I'm going over here. Any other place? Let's say from here I can go to over in this direction. Oh, yes, right now. So I can go over here. 2, 2 is there. Wait. So from here I went to either I can go here or I can go over here. So let's take this path only. If I take this path, so 2, 2 is there. I am taking over here 2. So any one of them. So let's take this one 2. So I reached at this point. So when I'm at this point, what is the path that I took? Again, one of them, same values. So let's proceed on this path is only. Then here I got 3, right? So why I got 3 over here? Because I took this maximum. So let's proceed in this path only. And after here I got a common thing. So this is one equality. So now this is one path, and from here I can go to the end. Both these cases doesn't make a sense. So this is one path to reach the end. This is one path. There can be other paths as well. You have to
like
think.
from 4, 5 to 3, 4. So like from the bottom when we start and we go diagonally.
From bottom.
Like fourth column, fifth row.
4, 5. Okay. Here then fourth column.
Sorry, third column, fourth row.
Third column is here, and fourth row 1, 2, 3, 4 here.
It's C वाला जो row है.
This one, right? Okay. This
So
one
you
where?
start with 1, then you go to 2, then you go to 3, then you go to 4.
Yeah, that is one thing, right? That is already marked. That's what I mean. This path, this red path.
Other one, the one just above it.
Okay, so 1 from here you go to here, you go to 1, and from here you want to go this part, right? So you cannot go over here because you did not take this one, did not happen because of this one. This one happened because of this one or this one, any one of them, because both of them are 1. You can only take the path where it is. So tell me this thing, how did I get this one?
Because of taking minimum of 1 and 1.
Maximum, right? Maximum of either this or that. Either of these two I took. So if I'm taking either of these two, I cannot go in this path, right? This means only when I'm taking this one into consideration. If I'm moving from I plus 1, j plus 1 to this one, that then only we will consider this diagonal movement. But I'm not taking that. If I would have taken that, then this should have been 2. Because in a diagonal movement, always I'm adding by 1. Right? So this path is invalid. So this is invalid. Whenever you are considering the sideward value, so let's say here, I took the side, here, see, 1, 1 is there, and here 1 was there. So I took this diagonal approach. Why? Because from 1 plus 1, I have done 2. But after that, when I reached over here, see, I did not go like this. This is wrong. Why? Because this 2 is there because of this 2 is there because I took either this path or this path. corresponding to this one of these two. So in this example, I took this one. You could have also gone up as well. That doesn't make a difference. So that's why this is wrong.
Finally, which one will we take as the
Now
total answer?
coming exactly, so now coming to that point, so you have multiple such paths possible, and what we are more concerned about is the equality part in each of this path, right? So let's take this one, this upper one, right? So if I take this upper path, so I have from here one diagonal is there, so which is corresponding to T, so write T. Then if I'm taking this, let's highlight it, I want this path. This is my current path under consideration. So first I've got one diagonal entry in this path, which is corresponding to the TT match. Then whenever I'm getting the next diagonal, tell me. So this is the next diagonal work that I'm getting. So which is corresponding to E. Okay. Then again I proceeded in this direction. This is the next diagonal is this one, which is for S. And then I'm not getting any diagonal movement. Okay. So now take the other path, which is, let's say, in green color I'm marking. Sorry. What's happening? I'm in this path, okay. Yeah. So if I take this green path now, then what are the diagonal entries? First, the same thing happens. T is there. After that, I'm moving in. So this is the first diagonal, which is corresponding to C. Yeah, corresponding to C. And then this is the next diagonal, which is corresponding to E, right? And then again one diagonal, which is corresponding to S. And then there is no other diagonal. So in these two paths, I find this is 4 length subsequence and this is 3 length subsequence. Both of them are subsequence. Both of them are valid subsequence, right? But among them, sect is the larger one.
So like 4 is giving the length of the longest subsequence. So you have to gradually trace back the path from 4 to 3, from 3 to 2, from 2 to 1. And
Not
from
4.
1 to 0.
How did you get 4?
4 is there, na, sir. It's the
That is the length.
largest value.
That
It's
is
the
the
length
length
of the longest subsequence.
Yeah, but that
So-
yeah, that is fine. But what you will have to do is basically trace back the path. But you should not say 4 or something. Basically, you have to trace back the path from here. So this cell, or let's say if you want to follow the path, you can follow it from this cell. Okay, so you have to follow the path that you have along the way and trace back whenever there is a diagonal entry.
And the diagonal entry should increase the number.
That is by definition. Any diagonal entry you will only take when the increase, the increase will only happen when you take a diagonal entry. By definition, diagonal entry means 1 plus LCW of I plus 1, J plus 1. That's what I said, right? When did the diagonal entries happen? See
They occurred because yes, it is equal. Yes.
Right? This is the diagonal entry, I equal to Bj, and then on this will only happen. This I plus 1, J plus 1 means diagonal. Right? If any one of them is not changing, both of them, I plus 1 has to be there in both the case for it to be diagonal. So this diagonal is only happening in this case when it is matching, and that is corresponding to by addition of one value. In other cases, when it is not matching, then diagonal will not be there, because see, this is changing but J is not changing. Again here J is changing, I is not changing. So they are not diagonal. And here I am not adding by 1. So diagonal happening of the diagonal means that I am adding by 1. And second thing is, I am only taking diagonal entry when there is a match in the characters.
So, sir, bring that matrix back.
Yeah.
So what I am observing in this green path is that when there is a diagonal entry, when there is a diagonal entry, the entries on the I plus 1 and J plus 1 side are less than the number on Ij. That is, 4 is greater than 3 and 3.
Yeah.
And those are the entries which we have to take. Like for 4 is there 3 times here, which 4 we are taking the 4, the diagonal entry where the I plus 1j and j plus 1i entries are lesser than 4.
No, nothing like that. See, don't think in that manner. The way that you have to trace back is, it's not like that you form the matrix and you say where it is one. Don't think in that term. Whenever you are calculating this, see in the code, whenever you will get this condition, right? Some point this condition will hold, right? LCW of this AI equal to BJ. Whenever happens, you will write this. This means you are taking a diagonal entry. Whenever this happens in the
But
code,
this you take multiple times. Now you take for substrings, other substrings also you take this entry.
where
For example, as I said, in the yellow one also you are doing this. For example, in column number 4 and row number 3, the entry has increased from 1 to 2.
yeah.
The entry has increased from 1 to 2, but we don't take this entry now because it is not the longest subsequence.
Okay, no. See, not that. So, fine. That it is not longest subsequence, but that will be taken care of by the max variable which you are using. So that's why I told. So whenever in the code you are writing that max, only that max. Whenever your maximum is getting changed, then only you will append that into the list.
Okay.
You have that max variable, right? So that
Yes.
max will work that out for you. So now next thing is, this is simply filled up by following those rules, and this also I discussed. So see, this sec is one substring, sect is another substring, like that. Code is again simple, nothing, 2 loops followed by, if there is a match you followed the same, and if it is not, then LCS of this. In case of longest common word, this whole thing was replaced with 0, right? Okay. See, whatever path you go through, this max will take care of the longest one. So you don't end up with only sec. You will end up always with sect, which is the largest one, longest one, right?
Max is always LCS 00, right?
Yeah. That's why I'm considering 2 ways, right? This is going the upward and this is going the leftward side. So I'm considering whichever is maximum, I will consider that. So you don't have to worry about which path is the longest. Max will take care of that. Only thing is, if you want to report that what is that subsequence, then you cannot write it in this fashion, because in this case you don't know whether I took LCS of R plus 1C or RC plus 1. So there you have to separate it out and figure out which one is max, and the one which is particular max, you have to track that out and append it to the list. That's it. So basically you have to use some if statement to check which one is greater and consider that. Okay, so again this is same, 2 loops is there, so mn into complexity, and there is nothing much. So longest common subsequence is done. Okay, next part is, I think, edit distance. Where is that? Give me a minute's time. We will resume after 1 minute. Just 1 minute. I have one task to do. Okay, fine. So the next thing is our edit distance, which is the third example. Edit distance problem is about that you have two, let's say two strings, and you want to change the first string into the second string. So you want to edit, uh, you want to, let's say in this example, here I have the two strings, or the strings are basically given as two paragraphs. This is one paragraph, this is one paragraph. So I need to change the first paragraph into the second one. Okay. So yeah, fine. So that is what we call editing a string. But the thing distance, what do we mean by the distance part? Edit distance means how many operations do I need to perform in order to convert the first string into the second string. And the operations are defined as there are three different kinds of operation. The first is simple substitution, right? So if we take a smaller example, so let's say I have a string ABA, and I have another string, let's say ACA, or wait, let's say uh, ACABA. Fine. Suppose I have these two strings, ABA and ACABA, and I want to convert the first string into the second string. So I need to convert ABA into ACABA. So the number of operation, minimum number of operation that I need to do that is what we call the edit distance. So edit distance would basically be a numeric value which would indicate how many operations I need to do on the first string in order to convert it to the second string. And that would be obviously the minimum number of operations required. So the minimum number of operations required to convert the first string into second string is basically the edit distance of this pair of strings. That is the definition. Now, what are these operations that I'm talking about? There are three different kinds of operation. The first is insertion of a character, second is deletion of a character, third is substitution of a character. All of this is happening in a character by character mode. So either I can remove one character, I can add one character, or I can substitute one character for another character of my choice. So these are the three operations defined, and by using these three operation in an optimal manner, I have to convert the first string into second string with minimum number of operations, right? So where is the notion of minimum and maximum number of operation, or difference in number of operation is coming? So the thing is, let's say here, if I need to convert the first string into second string, there at first what I can do is either I can add two characters in the first string. Okay, one important point, I will not make any changes in the second string, or my target is to convert the first string into second one. So whatever changes or whatever operation that I have to do, I will do it on the first one. So how can I make the first string into the second one? As you can see just by visual inspection, that I can add one A and one C over here in order to make the first string into the second string. So that would take two operation corresponding to two addition, right? So that is one option. Or I could have also done something like this, which would be a wrong way to go. But let's say if I do first AA is matching, right, then BC is not matching, so substitute B and C. So for B I will substitute C, so that is another operation. So in place of B I will write C. Then again AA is matching, so one corresponding to one substitution has already been corresponding to this B, one substitution has already been done. Then AA is matching, then one B is there, but here I do not have anything, so let's add one B and then one A over here. So for this, I added one addition. Here I had one addition. So now in this approach, I need three operation. Two addition, one substitution. Instead of that, if I would have ABA was earlier there, right? Instead of doing this, if I would have simply added A and C in the front, so that would have taken me only two operation. Getting the point? So that is the difference. So same string, if you want to convert into the other one, there are multiple ways to do that. I mean, you have different combinations of these three operations to be performed upon the first string to convert it into the second string. The difference is that you have to do it in a tricky manner, in an intelligent manner, so that you do not use many operation. The question's main motive is to find the minimum number of operation need to convert the first one into second one. Okay, so this is the whole context of how the problem will work. Is there any doubt in that? We can address that, or we'll proceed forward. Okay, fine, no doubt.
So, but like, is it
Go ahead.
like there are some tools which paraphrase, so they work in the same concept, or is it?
Exactly. They find the minimum distance, and also basically, so sometimes in GitHub, if you one feature is there that you it suggests you for auto corrections, that if you have some, I mean, let's say you had a last push of something, some work you have done, and there might be some errors in your some, let's say, syntax error, or let's say some, I mean, you messed up writing some code, some part of it, which is not logical part, but let's say some syntactical, or let's say some spelling mistake, that kind of thing. So it will suggest you that, okay, these are the changes that you have to make. Or even forget about GitHub and all, even in your notepad and all those, some notepad software, as you said, you get a suggestion that they are auto correction feature. So those things work by this edit distance concept. So basically the auto corrections happen by checking out the corrections possible with minimum edit distance. So which wherever there the edit distance is minimum, that means that word is very near to your word, and most probably you were trying to write that word but instead wrote the wrong one. So that's how the auto corrections work. So okay, so let's come to the edit distance. So since the context now is clear, now we will see how this edit distance is working. So let's go to the recursion statements. This is not the one. Okay, so sorry for that. So here, this is the first string u and this is the second string v. I need to convert u into v. Okay, and again, if ai equal to bj, so anytime if I get this condition, if ai equal to bj is holding, that means what? That means there is a match. So if there is a match, I don't need to edit anything, right? So I basically, if I consider a string like this, so let's take right, suppose these are the two strings, and if I see that there is a match between a and a, so this is my I variable and this is my j variable, right? So ai equal to bj. Okay, ai means, don't consider, I mean, a b in this term. So what I mean is basically the ith position, this okay, wait, what I mean is, let's use some other characters, otherwise it may get confusing. So let's say x, y, z, x, x, y. Fine. So this is basically your ai and this is basically your bj, suppose. So your ai and bj is equal now, x and x. So I need we don't have to make any change in the, I mean, any operation. It is fine. So when I told you everything happens in all this example, we go from right to left, right? So corresponding to the position when I am at this ai and bj, which is the leftmost x, and this xx is equal. So the number of operations required, the to convert the first string u till ith position of u and into j till jth position of j, that is equal to what? Whatever number of operation I required earlier. I no need to make any, I don't have to make any new operation to convert ai into bj because they are anyway equal. They are equal to the value x. So since I don't need to do any separate operation to convert the ai into bj because both of them are same, that's why the edit distance of ij, ed of ij is basically equal to whatever be the number of operation required earlier. Earlier means till I minus 1, sorry, I plus 1, j plus 1, which is basically this part, right? This whole part. So that's why edit distance of I plus 1, j plus 1. Okay, whatever number of operation was required. So that is done. Now, if it is not equal, then we have to take care of the correction, right? There are 3 operations and take care which one is better. So since there are 3 operations, any one of them I will be doing on this current string. So since one of them I will be doing, I'm adding 1 plus, right? So corresponding to one operation, 1 plus. And then I told you that we will have to choose that operation which takes minimum number of, I mean, which creates minimum number of operation in the totality. So that's why I write min. And then I have 3 different expressions corresponding to the 3 operations. So let us see how these expressions work. Suppose one string is x, y, x, and v is x, x, x. Right? So again, as I have already given you the example that in some certain strings, certain operations works better. Certain operation will do it in a lesser number of steps. So here if I see that 1x is there, so it is a match. Then y is there and x is there. So it's not a match. So either I can do addition, substitution, or deletion. So let's say I decided to go for addition. So if I take addition, so at first in order to make, I mean, change this string u into v, I have to add 1 x here. So that is one addition happened, one addition. Okay, then I see that 1 y is there, but here I don't have any y. So I have to delete 1 y. So one deletion would be there. Right? And then I get an x. So it matches. So 2 operations is required. But instead of doing one addition and deletion separately, what I could have done is simply do the substitution of this y with this x. So simply this y changes to be an x. So which corresponds to what? Substitution. Fine. Now, when I'm substituting this y and x, suppose I was at, this was my ai and this was my bj, right? So when I'm substituting ai and bj, so that means this part has been become, I mean, they have matched, correct? So what is the next thing that I have to do? I just have to move forward in both the places. That means basically whatever was the number of operation earlier to that, both I plus 1 and j plus 1, I will move forward in both the places. So I will go to check here, and in this area I will go to check here, because this I have substituted. Substituted means this has become already equal. So if these two are equal, I will go to the next character in both the strings. That's what I'm doing. So that's why it is equal to I plus 1 and j plus 1. That's I'm going to check on both the strings. I will proceed one further because I've done substitution. Substitution means that ith and jth part has already become equal. There is no difference between them. It has been substituted. Now I will check.
Right to left, no, sir. We will go from right to left.
Yeah, I will go from right to left only. What I meant is I will. So this ed of ij, this is the left part, and this is the right. Sorry, this one is the right part. Basically, I'm moving from here to here. That's why to calculate ed of ij, I'm needing this ed of I plus 1, j plus 1. I need this. So, but what does it mean? Because I'm substituting this I, bi, and ai and bj, right? That means this is same. This is equal, and whatever was earlier in both the string, that's what I need. I mean, that is earlier in both the string mean number of operations required to make both the strings similar in early and just one step ahead, I mean previous, which is basically ed of I plus 1, j plus 1. Same concept which we applied over here. Okay. So if you got confused, let me just say it in this manner. What I mean is, since you are doing substitution over here in this area, that's why I am going to check. I mean, that's why I am thinking of that whatever step was earlier to this step, earlier to this substitution, I have exhausted. I mean, both. I mean, I have reached to the just the previous character on both the string when I'm doing substitution. I will tell you why. So let's take the addition example. You will understand what I mean. So let's take, instead of substitution, if I would have added instead an x here, right? So this would look like xx, y was there, and x, and this would look like xxx. This, instead of substituting the y, I have now added one x. Suppose I would have taken the path of addition like the previous discussion instead of substituting y with x. In this case, where was ai? I mean, the one that was ai was there. So where was ai? Ai was at this part, right? Now I have done the addition, and this was bj, right? The addition happened at ai, which is basically x. X is added, and this is your this x is your bj. Now the thing is, since I have added one, I am this y is yet not explored. That's why, because of that reason. Okay, so that means I have to check for whatever was j. I mean, I have to check for the next character over here. So I need to take care of this whole thing. I cannot move this bj forward. Okay, so x is added, that is fine. But due to this addition, I have to still take care of this y. This has not been taken care of, right? So I cannot move forward in this string now. I have to take care of this y. So I cannot do I plus 1, j plus 1. Okay, I can only, I have to stick with this I here. So I only can move j. I can move forward with j, but I cannot move forward with I because this y is still there. So I have to take care of this y at I. So I j plus 1 is the term corresponding to addition. I cannot move I because I have added something at the ith position, and now I have to take care of what was earlier. I mean, whatever before the addition, whatever was there earlier, I have to take care of that, right? So I cannot be moved further. I is still there. J plus 1, I can move forward with j because j part matching is done. Why? Because whatever was at j, I have added that. So this x is basically, this is basically bj, right? I have added this x because I got x over here, and bj is x. So I have added a bj at this position. But since I have added a bj at this position, this y is left over. This y I have to take care, right? So I cannot move forward with I now. I cannot write I plus 1. If I write I plus 1, then that means I have to, I'm going at this x. But still this y is there. So I have to take care of that y, right? Because it is not supposed to be there. So that's why I cannot move y. I will move j, and next I will check whether the next character of j, that is the j plus 1th character, is that equal with that y or not. So whether that j plus 1th character is equal to I or not. So bj has been added. Ai and bj are there. Bj has been added in place of this, I mean, at this point. Okay, so all I need to do now is I need to check whether the I which I had earlier, that is this y, right? Ai which I had earlier, that is this y, whether that is matching with bj plus 1. Bj and ai was not matching. So I added a new bj. I added a new bj explicitly, but since I added a new bj, my bj matching has happened, right? But my this ai that corresponding to this y, I mean, this y is still there, which I have to take care. So that's why I will not move I further. I will stick with I because to take care of this y. But since bj matching has already happened, I can move bj one step forward, and that step I will compare whether that bj plus 1 is equal to this y or not. That is equal to ai or not. If it is equal, then I don't have to do anything else, right? But if it is not equal, then I would be in trouble. Then I would have to delete or do something else. Basically, in this case, I will delete it. Now, when it would be beneficial to do this addition? So let's say I had something like the x, y, x, and x, y, x. Suppose this is u, this is v. Now in this case, you see, in this case, if I did this exact thing, right? This is the exact example. So this xx was matching ai bj. So I move for, I consider both forward. So then I come to this iteration y and x. I say y and x is not matching. Now since y and x is not matching, what I would do is I am taking the addition path. I am not taking substitution path. I am taking addition path, just like this. So since I am taking addition path, this is your bj currently. This x is bj. This y is ai. Let me take another color. So this is your ai and this is your bj. Now since ai and bj are not matching, what I do is I add a bj in this position. Add a bj means in this position I add one x. Correct. Now since I have added this x is what? X is corresponding to this bj. So since this bj has already been matched with this new value, because that's what I have added explicitly, I have added the bj value over here. So that bj and this bj has matched basically. But this y was the actual character, which was a mismatch. So I cannot totally ignore this y. I have to stick with this y and check whether this y, what to do with this y. Should I delete it in the next step? Should I do substitute in the next step? What do I need to do? So therefore I cannot move ai now. Okay, but I am sure that this bjx has been matched because I have added one character over here corresponding to this bj. So therefore I can move forward with bj now. So therefore I'm moving forward with bj plus 1, right? And then I am checking whatever was ai was, because I cannot move ai further. I have to check what to do with this ai. So I stick with ai, move forward with bj. So bj plus 1 and ai. Now see, fortunately I see that ai and bj plus 1 is matching. yy is there. So now since this is matching, I don't need to change anything. I can directly move forward. So I move forward and then again I see xx is matching. So it's a beautiful thing. So simply by, so this string becomes xxyx, this string is also xxyx. So simple by one addition, I converted the first string into second string. But if I would have gone to substitution in this example, then this would have been a bad situation. Why? Because in place of this y, if I would have substituted x, right? So I would have got xxx and then again one y would be there. So according to this y, again I have to add one y addition. So one x for substitution and then y addition. So two operation would have been required if I would have taken the first y for substitution of x. But in this example, if I take one addition of x, then only one operation we can convert the first string into the second one. Right. So this is the point of addition. So when I'm adding something, I can be sure the bj part is over because I have added the bj part itself. Right. This is bj only. X is this bj only. But ai I have ignored. So I will stick with ai as of now, and I will check whether the next bj, basically bj plus 1, whether that is equal to the ai which I have ignored in the previous step. Okay. So that is the point. So basically when you do addition of a character, that corresponds to edit distance of I remains at its own position, j gets changed by 1. This is your addition. Deletion means what? Just the opposite. ed of I plus 1 j. And when you substitute, that basically means both of the things become same. So I move forward in both the strings. So that is ed of I plus 1 j plus 1.
So the string which is to be edited has to be kept on the x-axis or on the y-axis.
That that depends on the implementation of your code. But in this example, I think. Wait, let me just check. Okay, so in this example, we are considering u as the string, right? So ai basically is on your y-axis. Right, u is on your y-axis, but that doesn't make a difference because if you write the equations properly, it would work. No worries. Fine. So okay. So as I told you, the meaning of these three relation. These are the three.
In V would not like we are inserting only on U, or we are going to insert in V
No,
as
no, 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 no. Only whatever operations you are doing it on you. I have
Okay.
told that in the start only. Okay. So always please when you see the sessions again on YouTube, hopefully you will just see whatever I'm telling at the first, because those are the prerequisite condition. Otherwise you will get confused on the later part. So
Say in case of delete operation, so like
okay.
in case of insert, it is clear that we will be moving forward
With
if
B,
as
BJ
long as,
plus 1.
yeah, in BJ+1, as long as there are matches, right? But in case of delete, we are saying that it's I+1 and J.
Yeah.
So because we are deleting in U.
Yeah.
So how is that working?
Okay. So it's just I mean, reverse the situation, you will understand. So let's take so suppose this is the current situation, right? So currently I am at this is my AI, this is my BJ, correct? And this XY is there, it is not matching. Since it is not matching, suppose I went for deletion, right? So I will delete this X, everything happens on U, right? So I am deleting this X. So if I delete this X, so what is the next thing I have to do? This X was there which was not matching with this BJ, but that does not mean BJ has matched with any term, right? I can only move forward with BJ when BJ has already matched with something, right?
Okay.
So that's
Yes.
why BJ will stick it at its position, but I have deleted the current AI. That's why I
We
will
have
move.
to move to the next position.
That's it.
Okay.
Right?
Sir. Clear.
So that's why substitution for deletion, it is I+1 and J sticks at its position. Fine. Okay. So that's it. Now you have the three equations, and this one is for the equality. Code you have to just simply put this. Base case is 0. If you basically when you reach Mn, it's out of the boundary of both the strings, so you put it as 0. Okay, this is important actually. I forgot. Here, 3 of 3 base cases are there. So suppose one string is A, another string is A, C, A, B, A, C. So you want to convert, let's say, this string into this string, right? So let's say I do a substitution. For this A is matching, and this corresponding to this A and this C, I do a substitution. So that this A is substituted into C. A was there and a substitution happened. Let me write it in another color. So corresponding to this substitution, C is being inserted. Fine. One operation is done. But after that, what would be the current scenario? So my AI would be at basically, I would be at 3, right? Or let's say in terms of array, it would be at 2 position. Basically, this is equal to my I. Because I have already, this is 0, this is 1, and this is 2. Because I have now exceeded the limit of the string. And basically here I would be at this position and my J would be at this position, right? So this is basically nothing but your BJ currently. So at this point, how does this ED look? So ED is nothing but ED of your I is at 2 and J is at also 2, right? But the problem is now that I am out of the string for U, right? So U doesn't have any other character left over here. So that means U, suppose this is basically 2 is what? 2 is basically the length of U. So let's say length of U in this case is indicated with what? M, right? Length of U is M. So this basically ED2, 2 basically means in a general, general context, This is nothing but m comma 2. Right? So this means that when I have reached the end of the first string, there is nothing left. But still I have not converted it into the second one. That means the second one is a larger string, and I have to now add whatever character is there in the second one into the first string. So this is not editing. This is just, I mean, are we editing? But basically now I have no options of deletion or substitution or something like that. Only option is I will simply add, right? Insert whatever is left, or how many number of characters is left, I will insert. Simply copy paste. So basically this whole part from here to here, you do a copy paste and paste it, copy and paste it over here. So that is insertion. So whenever ed of m comma 2, or in this case 2, basically what this means is ed of m comma j happens, ed of m comma j happen, that means I have to insert whatever is there in the v string. So how can I know how many? So basically you have to do insertion. Now how many insertion? Whatever is the number of character left in v. How can I get that? Simple, right? So if you have whatever is the length of your v minus where you are presently there in v, right? So I am currently in this position b of j, so I am at j, and the total length of this v string is n. So n minus j would give me the number of characters that I have to add in u, right? That I have to add in u. So this ed of m comma, so in that general sense, this is equal to j minus 2, n minus 2, or in general sense ed of m comma j is equal to n minus j. You can see this. Fine. So this is corresponding to addition of the extra letters which are left, right? Similarly, just the other way around, flip around this concept and you will understand why this is m minus I. Right? When this is deletion, when the first, just flip around. So basically, this is your v and this is your u. Right? So after the first substitution, you are at this, so this is your ai, and your bj is now out of the string. So this is your bj, which is currently at this empty position. So j equal to 2. Same concept, just the other way around. So since AC is already matched, so whatever is present over here, you have to delete this, right, from the u. So how many characters are present here? N minus or m minus whatever is the length of u, which is m, right? Length of u is m. So m minus I is basically the number of characters present over here, which you have to delete to convert u into v. So therefore here m minus 1 deletions is required. Okay, so when it is I comma n. So that's it. Those are the cases. On the basis of that, we will fill up this boxes. Right. Okay. So whenever there is a match, as you can see over here, whenever there is a match, so let's say this EE is a match, right? So this EE is a match. So whenever there is a match, what will I do? If it is a match AI equal to BJ, so then I will simply copy the value of I plus 1 J plus 1, which is this. So that's why I'm simply copying I plus 1 J plus 1 over here. Whenever there is a mismatch, so let's say S comma E. So here I have a mismatch. Okay, or let's say I comma E. So here I have a mismatch 3. So here I have to consider that which one is minimum among these 3. The one which would be minimum, add 1 with that and place. So here I can see 2 is minimum. So for 2, I will add 1 and place over here 3. Fine. So that's this. These 3 are basically the 3 operation that you do. So this corresponds to what? This is your I. If this is your I comma j, right? So let me just. If this is your I comma j part, so that this means this area is what? This area is I plus, sorry, I plus 1, yeah, I plus 1 comma j, and this is your I comma j plus 1, right? So as you can see that this I minus I plus 1 j, which means this is insertion, this is deletion. and this is substitution. So from these three, whichever is the minimum one, you will take that and add 1 with it and place it over here. See, 2 is minimum, so 2 plus 1 is 3. Fine, according to the recursive relation that we had. This same recursive relation. Everything is done on the basis of this recursion. See, minimum with these three, you do it. Okay, fine. Yeah, nothing else. You simply put it in that way, and that's it. So your this edit distance is done. One other algorithm is left, which is matrix multiplication. So that hopefully we will do in the next session. Okay. So in matrix multiplication is the only algorithm left. We will do that in the next session, in the Friday session. So any doubt in the edit distance? Anything? Okay, fine then. Thank you everyone for joining. Good night.
Thank you, sir. Good night.